You are already comfortable. You are already somewhere safe and warm, and the weight of the day is beginning to lift, beginning to fade into the background where it belongs. The room around you is quiet, or quiet enough, and the light is low, and your body knows what to do now. It knows how to let go, one small muscle at a time, one breath at a time, sinking a little deeper into the surface beneath you. There is nothing you need to solve right now. There is nowhere you need to be. For the next little while, the only thing that matters is the sound of a voice, and the slow, gentle unfolding of an idea. That idea is something you use every single day, something you have used for your entire life, and yet it is something most of us rarely stop to think about in a quiet, unhurried way. It is there when you turn on a light. It is there when you press a button and music begins to play, or when the screen of a phone glows softly in the dark. It is there in the hum of a refrigerator, in the warmth of a blanket on a cold night, in the tiny spark you sometimes feel when you reach for a metal doorknob, electricity. It is so woven into the fabric of daily life that it becomes almost invisible, like the air itself. And because it is invisible, because you cannot see it moving the way you can see water flowing in a stream, it can feel a little mysterious. It can feel like something you are not meant to understand. But that feeling, that small sense of distance from the thing itself, is something we can let go of tonight, very slowly, very gently, without any effort at all. There will be no equations in what follows. There will be no memorization, no tests, no moments where you need to sit up and pay close attention. This is not a classroom. This is more like a walk, a slow, unhurried walk through a landscape you already know, except tonight, we are going to look at it from a slightly different angle, with a little more patience, a little more willingness to pause and notice what is actually happening under the surface of things. Imagine yourself walking down a familiar road, one you have traveled 100 times before, but this time you are walking at dusk, and the air is cool, and you have all the time in the world. You can stop and look at the way the wires cross between the poles. You can notice the soft glow of a street lamp as it flickers on. You can wonder, in a lazy, aimless way, what is actually traveling through those wires, what is actually making that light possible. And then you can keep walking, letting the thought drift in and out of your mind without needing to hold on to it too tightly. That is the spirit of what we are doing here. A gentle unfolding, a slow, patient unwrapping of an idea that has been understood for a long time by many people, working over many generations. Electricity is not a new discovery. It is not something that scientists just figured out last week. It is old, settled science, built up piece by piece over centuries, and there is a quiet comfort in that. The knowledge is solid. It does not shift under your feet. And because it is solid, you do not need to brace yourself for surprises. You can simply let the words wash over you, trusting that each idea will be introduced slowly, repeated gently in slightly different words, and left to settle before we move on to the next one. So if you find your attention drifting, let it drift. That is not a flaw in the process. That is the process. A half-asleep mind does not need to grasp every word. It only needs to feel the general shape of the ideas, the broad outline, the soft rhythm of one thought leading into the next. If you miss something, it will come around again, stated another way, just as gently as before. There is no rush. There is no deadline. The only goal is to let your mind rest on something calm and steady, something that does not demand anything from you, something that simply exists, like a quiet hum in the background of your awareness. Let us begin with the simplest possible starting point. Everything you have ever touched, everything you have ever seen, the chair you are sitting on, the air you are breathing, the water you drank earlier today, the pages of a book, the screen of a phone, the fabric of your clothes, the bones inside your body, all of it, every single bit of it, is made of tiny, tiny building blocks. These building blocks are so small that you cannot see them with your eyes alone. You cannot see them with an ordinary microscope, the kind you might have used in a school science class. They are smaller than that, far smaller. They are the smallest unit of ordinary matter, the smallest piece of something that still behaves like that something. These building blocks are called atoms. The word atom comes from an old Greek word that means uncuttable, something that cannot be divided any further. And for a long time, people thought that was true, that atoms were the absolute bottom layer of reality, solid little spheres with nothing inside them. But as time went on, as people looked closer and closer with better tools, they discovered that atoms themselves are made of even smaller parts. They are not solid spheres at all. They are mostly empty space, with a few tiny components arranged in a very particular way. Picture, if you like, a vast, quiet stadium, completely empty, with a single pea sitting right in the center of the field. That pea, that tiny dense speck in the middle of all that open space, is something like the center of an atom. The center is called the nucleus. The nucleus is made of two kinds of particles, but we do not need to separate them in our minds just yet. What matters is that the nucleus is heavy, and it is dense, and it sits right in the middle, holding most of the atom's mass in a very small space. And far away from that nucleus, relative to its size, are even tinier particles. These particles are so light they are almost weightless, and they move around the nucleus in a kind of cloud, a kind of haze of motion, too fast and too spread out to pin down in one exact spot. These tiny, light particles that orbit the center are called electrons. Now, electrons have a particular property, a characteristic that is very important for everything we are going to talk about tonight. This property is a kind of charge. Charge is a word that can sound technical, but the idea behind it is very simple. There are two kinds of charge, and they behave in opposite ways. One kind of charge pulls toward the other kind. The other kind pushes away from itself. You have felt this push and pull in your own life, even if you did not have a name for it. You have felt it when you rubbed a balloon on your hair and then tried to pull it away, feeling that strange, sticky attraction. You have felt it when you walked across a carpet in wool socks and then reached for a metal doorknob and felt a small, sharp spark jump from your finger. That is charge at work. That is the push and the pull. The two kinds of charge are called positive and negative. The names are not important in themselves. They could have been called red and blue, or north and south, or anything else. What matters is that they are opposites. Positive charge and negative charge attract each other. Negative charge and negative charge push each other apart, and the same is true for positive and positive. Like kinds push away. Unlike kinds pull together. This simple rule, this basic push and pull, is at the bottom of nearly everything we will explore tonight. In the nucleus of an atom, at that dense center, there is a kind of particle that carries positive charge. These particles are called protons. The number of protons in the nucleus determines what kind of atom it is, whether it is an atom of oxygen, or an atom of carbon, or an atom of iron, or an atom of gold. And orbiting around that nucleus, in that vast empty space, are the electrons, which carry negative charge. In a normal, balanced atom, the number of electrons orbiting the outside exactly matches the number of protons in the center. The positive and the negative are equal, so the atom as a whole has no net charge. It is electrically neutral. It is balanced. Most everyday objects are like this. The chair you are sitting on is electrically balanced. The blanket you are under is electrically balanced. The glass of water on the bedside table is electrically balanced. In each of these things, the atoms are arranged in their own particular patterns, but across the whole object, the positive and negative charges cancel each other out. There is no overall push or pull. There is no spark waiting to jump. The object just sits there, quiet and still, as objects do. But that balance can be disturbed. It is possible under certain conditions for electrons to be moved from one atom to another, from one object to another. And when that happens, when an object has a few extra electrons or is missing a few electrons, it is no longer balanced. It has an overall charge. It is either negatively charged if it has extra electrons, or positively charged if it has lost some, and that charge wants to correct itself. It wants to return to balance. It wants to push or pull until things are even again. This is the seed of everything. This tiny imbalance, this gentle pressure toward balance, is what lights up cities and powers motors and sends signals through the nervous system of every living creature. It is a force of nature, as basic and as old as gravity, and it operates by the same patient logic. Water flows downhill because gravity creates a difference in height, and the water wants to even out that difference. Charge flows along a wire because an imbalance creates a difference in electrical pressure, and the charge wants to even out that difference. The language is different, but the idea is the same. A difference, a flow toward balance, a settling. We will return to this comparison many times tonight, the comparison between electricity and water. It is an old comparison, one that engineers and teachers have used for a very long time, because it works so well. Water is something we can see and feel. We understand what it means for water to flow downhill. We understand what it means for a pipe to be full or empty, for pressure to be high or low, for a valve to be open or closed. Electricity behaves differently in many important ways, but the basic picture of something flowing from a place of higher pressure to a place of lower pressure, moving through a path, doing work along the way, that picture holds. It is a good picture to keep in the back of your mind, a soft mental image to return to when the words start to feel abstract. So here we are, at the very beginning of the trail. We have the idea of tiny building blocks called atoms. We have the idea that atoms have a heavy center with positive charge and light orbiting particles with negative charge. We have the idea that these charges can be balanced or unbalanced, and that an imbalance creates a kind of pressure, a kind of push towards settling. These are the only pieces we need for now. These are the only ideas we need to hold gently in our minds as we drift forward into the next part of the walk. You do not need to remember any of this. You do not need to quiz yourself on the difference between a proton and an electron. If you are still awake, and if you are still listening, just let the shape of the ideas sit with you, the tiny dense center, the light orbiting particles, the two kinds of charge, the push and the pull, the quiet, patient tendency of all things to seek balance. These images will be here when we need them again. They will rise up naturally as the story continues, and each time they do, they will feel a little more familiar, a little more like something you have always known. For now, let the words grow softer. Let the space between thoughts stretch out a little longer. The night is still, the room is still, and somewhere, in the walls around you, in the wires hidden behind the plaster and the paint, a quiet, invisible something is waiting. It is not mysterious in a frightening way. It is just there, like the water in the pipes, like the air in the room, a part of the ordinary world, ready to be understood. And we will understand it, slowly, gently, one small step at a time. But there is no need to take the next step yet. For now, just breathe, just listen, just settle in. The walk has only just begun, and it will continue when you are ready, in your own time, at your own pace, into the soft and welcome dark. The soft and welcome dark is still here, holding everything gently in its place. And as we ease forward, taking one more small step along this quiet path, we can begin with something very simple, something so basic that it underlies every single thing you have ever seen or touched. The screen of the device you may be listening through, the pillow beneath your head, the air moving softly in and out of your lungs. All of it, every bit of it, is made of the same kind of tiny building blocks, arranged in different patterns, like the pieces of a vast and patient puzzle. These building blocks are called atoms. The word itself is old, much older than the science that eventually came to understand what atoms actually are. It comes from a language spoken thousands of years ago, and it means something that cannot be cut, something that cannot be divided into smaller pieces. For a very long time, that is what people believed atoms were. The smallest possible unit of anything. the final, indivisible bottom layer of reality. A solid little bead of stuff, with nothing inside it, no structure, no parts, just a hard and permanent thing. That picture turned out to be incomplete. It was a useful picture for a while, and it helped people think about the world in a clear and orderly way. But as time passed and tools improved, as people learned how to look closer and closer at the fine grain of matter, they found that atoms themselves have an inside. They are not solid beads. They are not indivisible. They are made of even smaller parts, arranged in a particular kind of architecture, and that architecture is the key to everything we will talk about tonight. Let us take a moment, a calm and unhurried moment, to picture what an atom actually looks like. Not with the eye, of course, because atoms are far too small to see, even with an ordinary microscope. An atom is so small that if you took a single grain of sand and blew it up to the size of a large mountain, the atoms inside that grain would still be tiny, far smaller than anything you could make out. That is the scale we are talking about. A scale so far below the world of everyday seeing that it can be hard to hold in the mind. And that is perfectly all right. We do not need to hold it precisely. We only need a rough sketch, a soft watercolor impression, something to guide the imagination gently forward. At the center of the atom sits a dense, heavy core. This core is called the nucleus. The nucleus is made of particles that are themselves quite heavy, at least compared to the other parts of the atom. These particles are of two kinds. One kind carries a positive charge. These are called protons. The other kind carries no charge at all. These are called neutrons. The protons and the neutrons huddle together in the nucleus, packed very tightly, held by a force that is different from the electrical push and pull we will spend most of our time with tonight. This force that holds the nucleus together is very strong, but it only works over extremely short distances. It is the glue that keeps the center of the atom from flying apart, since all those positive charges packed together would otherwise push each other away. The number of protons in the nucleus is what gives an atom its identity. One proton in the center, and you have hydrogen, the lightest and simplest of all the elements. 6 protons, and you have carbon, the element that forms the backbone of every living thing. 26 protons, and you have iron, the metal that runs through our blood and our bridges and our buildings. 79 protons, and you have gold, soft and heavy and unreactive, shining with a particular warm light. Every atom of a given element has the same number of protons in its nucleus. That number is fixed, like a fingerprint, like a name. But the protons are only half the story, and for our purposes tonight, they are the less important half. What matters much more for understanding electricity is what is going on outside the nucleus, in the vast and mostly empty space that surrounds it. Because orbiting around that dense central core, moving in a kind of diffuse cloud, are particles that are very different from protons. They are much, much lighter. In fact, they are so light that their mass is often treated as almost nothing, a tiny fraction of the mass of a proton. And they carry a negative charge, the opposite of the positive charge of the protons. These particles are called electrons. The word electron comes from the ancient Greek word for amber, that golden, fossilized tree resin that the Greeks noticed could be rubbed with fur to produce a strange, attractive force. That force was static electricity, though they did not have a name for it yet. The connection between amber and the electron was made much later, when people began to understand that the strange force was carried by tiny charged particles. The name stuck, and so we have electrons, the light, negatively charged particles that orbit the nucleus of every atom. Now, in a normal, balanced atom, the number of electrons orbiting the outside is exactly equal to the number of protons in the center. The positive and the negative balance each other out. The atom as a whole has no net charge. It is electrically neutral. It is at peace, in a manner of speaking. This is the natural state of most atoms in most everyday objects. The chair you are resting on is made of atoms that are electrically balanced. The water in the glass beside you is made of molecules, which are groups of atoms bonded together, and those atoms are electrically balanced. The air you are breathing, mostly nitrogen and oxygen, is made of balanced atoms. All of this ordinary matter, the stuff of daily life, is electrically neutral. It does not spark. It does not shock. It just sits there, quiet and still, holding its electrons close. But here is the thing that makes electricity possible. Here is the small detail that turns out to matter enormously. Those electrons orbiting the outside of the atom are not all held with the same tightness. In some materials, the outermost electrons are held very loosely. They are far from the nucleus, and the pull from the positive protons in the center is weaker at that distance. These loosely held electrons can be moved. They can be nudged from one atom to another. They can, under the right conditions, be made to flow. This is the seed from which everything grows. A tiny imbalance, a gentle nudge, an electron that moves from one atom to the next, leaving behind a slight positive charge where it departed and creating a slight negative charge where it arrived. And because positive and negative charges attract, because they feel that pull toward balance we described earlier, the movement of one electron can create a kind of pressure, a kind of invitation for other electrons to follow. One moves, and then another moves, and then another. And before long you have a drift, a current, a slow and steady progression of charge through a material. But we are getting ahead of ourselves. We are still building the picture, laying down the first layer of understanding. Before we talk about movement, we need to sit a little longer with the idea of the atom itself. We need to let the image settle into the mind, soft and clear. The tiny dense center with its protons and neutrons, the cloud of electrons far away relative to the size of the nucleus, orbiting in layers, in shells, like the rings of a distant planet. And the fact that the whole thing is mostly empty space. That is worth pausing on for a moment, because it is one of those quiet truths that can shift the way you see the world. If an atom were blown up to the size of a large cathedral, the nucleus would be something like a small fly sitting at the very center. The electrons would be specks of dust orbiting far out in the vastness of the interior. Everything else, all that space between the center and the orbiting particles, is emptiness, nothing, a void. And yet, when you press your hand against a table, it feels solid. The atoms of your hand do not pass through the atoms of the table. They push back. That solidity, that resistance, is not because the atoms themselves are solid, but because of the forces between them. The electrons in the atoms of your hand repel the electrons in the atoms of the table. Like charges push each other away, remember, and so the table feels solid, even though, at the deepest level, it is a gauzy web of tiny particles separated by enormous distances. It is a strange and beautiful thought to fall asleep with. The world that feels so solid and substantial is, in fact, a delicate architecture of forces, a dance of attraction and repulsion, held together by the quiet, patient rules of electricity, the same rules that govern a lightning bolt, the same rules that govern the tiny spark from a doorknob, the same rules that govern the current flowing through the wires in your walls. It is all one thing. It is all one set of principles, working at different scales, in different materials, but always the same at heart. Let us return then to the balanced atom. Most of the time, the atoms around you are in this balanced state. The number of electrons equals the number of protons. The positive and the negative cancel out. The object made of these atoms has no overall charge. It is neutral. But this balance is not permanent. It can be disturbed. And when it is disturbed, when an atom gains or loses an electron, it is no longer neutral. It becomes what is called an ion. An ion is simply an atom that has an imbalance of charge. If it has lost an electron, it has more protons than electrons, so it is positively charged. If it has gained an electron, it has more electrons than protons, so it is negatively charged. Ions are everywhere around us, though we rarely notice them. They are in the air after a thunderstorm. They are in the water of the ocean. They are in the fluids of our own bodies, helping nerves send signals and muscles contract. An ion is just an atom with a story, an atom that has been through a small change, a gain or a loss, and is now carrying a little extra push or pull because of it. The fact that electrons can be moved from one atom to another is the foundation of everything we mean when we say the word electricity. It is the movement of charge. It is the flow of these tiny, light, negatively charged particles from a place where there are more of them to a place where there are fewer of them. It is the universe, once again, seeking balance, seeking equilibrium, seeking a state of rest. This is a good place to pause and let the image settle. The atom, with its dense nucleus and its orbiting electrons, the balance of positive and negative, the possibility of imbalance, the quiet potential for movement that sits inside every single piece of matter, waiting for the right conditions, waiting for a path to open. That potential is always there. It is in the air. It is in the ground. It is in the wires that crisscross the landscape, and in the battery that powers the device you are using. It is one of the fundamental properties of the universe, as basic as mass, as basic as gravity, and it operates with the same calm, impersonal consistency. In the next part of our walk, we will begin to look at what happens when that potential is released, when the balance is disturbed and charge begins to move. We will start with the simplest and most familiar form of this movement, the kind you have felt in your own body on a dry winter day. A spark, a small, sudden rearrangement of charge, a tiny bolt of miniature lightning jumping from your fingertip to a doorknob. That is where we are headed next. But there is no hurry to get there. The atoms will still be here, doing what they do, whether we think about them or not. The electrons will still be orbiting, the protons will still be holding their positive charge, and the quiet architecture of matter will still be standing, patient and unchanging, waiting for the light of morning. For now, let the image of the atom drift in your mind like a slow-moving cloud, the dense center, the orbiting particles, the vast space in between, the balance, the potential for movement. Let these words settle into the quiet of the room, blending with the sound of your own breath, the soft weight of the blanket, the gentle pull of sleep that is always there, just beneath the surface, ready to carry you forward into rest. The night continues, the world holds still, and somewhere, inside every atom of everything around you, the same quiet force is waiting, patient and eternal, for the moment when it will be called upon to move. The quiet force is always there, waiting, and sometimes, in the most ordinary moments, it stirs. Not in a steady, organized way, but in a sudden, brief rearrangement, a small, local disturbance of balance. This is the form of electricity that most of us have felt with our own bodies, the form that is closest to everyday experience, even if we do not always think of it as electricity at all. It is the spark from a doorknob. It is the crackle of a sweater pulled over your head. It is the way a balloon, rubbed against your hair, will cling to the wall as if by some quiet magic. All of this is the same force, the same push and pull between positive and negative charges, playing out in a way we can see and hear and feel. This form of electricity is called static electricity. The word static means standing still, not moving, and that is the key difference between this kind of electricity and the kind that powers a light bulb or a refrigerator. In static electricity, charge builds up in one place and stays there, at least for a while. It does not flow in a steady stream. It gathers, it accumulates, it waits, and then, when the conditions are right, it jumps, it discharges, it moves all at once, in a tiny, brief burst, and then it is gone. To understand how this buildup happens, we need to return to the idea of the atom, and especially to those outermost electrons, the ones that are held most loosely by the nucleus. In some materials, these outer electrons are held so loosely that even the gentle friction of rubbing two surfaces together can dislodge them. One surface gives up some of its electrons. The other surface collects them. And because electrons carry a negative charge, the surface that gains electrons becomes negatively charged, while the surface that loses electrons becomes positively charged. An imbalance has been created, a difference in charge, a quiet electrical pressure waiting to be resolved. Think of a wool sock on a carpet. This is an image many of us know from childhood, or from cold winter mornings when the air is dry. As you walk across the carpet, the soles of your socks are rubbing against the fibers of the floor. That rubbing is enough, on a very small scale, to pull electrons from one material and transfer them to the other. Depending on the particular materials involved, the electrons may move from the carpet to the sock, or from the sock to the carpet. What matters is that they do not stay in balance. One surface ends up with extra electrons, the other ends up with a deficit. Your body, which is connected to the sock, takes on that charge. You become, for a brief moment, a vessel of static electricity, carrying around a slight excess or shortage of electrons, a small electrical imbalance distributed across your skin. And then you reach for a metal doorknob. Metal is a material that allows electrons to move very easily. We will talk more about that in the next part of our walk. For now, it is enough to know that metal provides a ready path for charge to flow. When your finger gets close enough to the doorknob, the difference in charge between your body and the metal becomes too great for the air to keep them apart. The air itself, which is normally a good insulator, a good blocker of electrical movement, breaks down for a tiny instant. A small channel of charged particles forms in the air, and the electrons jump. They leap from your finger to the doorknob, or from the doorknob to your finger, depending on which way the imbalance runs. That leap is the spark. That tiny, brief flash of light and the faint prickling sensation you feel are the charge equalizing, the balance restoring itself, the universe gently settling back toward neutral. The spark is very small, but it is real electricity. It is the same basic phenomenon that powers a city, just happening on a tiny scale, in an uncontrolled burst rather than a steady flow. The voltage involved, the electrical pressure, can be quite high. A spark from your finger to a doorknob can involve several thousand volts of pressure. That may sound like a lot, and in terms of voltage it is, but the total amount of charge that moves is so small, and the duration of the spark is so brief, that the actual energy involved is tiny. It stings for a moment and then it is over. Your body has returned to electrical balance, and the doorknob has returned to balance, and the world continues on as if nothing had happened. The balloon rubbed on hair is another gentle example of the same idea. When you rub a balloon against your hair, the friction pulls electrons from one surface to the other. Typically, electrons move from the hair to the balloon, leaving the hair with a slight positive charge and the balloon with a slight negative charge. Now the balloon is carrying extra electrons. It is negatively charged. And if you hold it near a wall, something interesting happens. The wall is electrically neutral, balanced, with equal numbers of positive and negative charges. But the negative charge on the balloon repels the electrons near the surface of the wall, pushing them slightly away, deeper into the wall. This leaves the surface of the wall with a slight positive charge, just in the area near the balloon. And since opposite charges attract, the balloon sticks. It clings there, held by the gentle pull between its own negative charge and the induced positive charge on the wall. Eventually, over time, the extra electrons on the balloon will leak away into the air, or onto the wall, and the balloon will fall. The balance will be restored. The static charge will dissipate, slowly and quietly, without a spark. These small, everyday experiences are the most direct way we have of feeling electricity with our own senses. They remind us that this force is not something distant or abstract, confined to power plants and wall outlets. It is a property of the materials around us, the clothes we wear, the floors we walk on, the air we breathe. It is always there, latent, waiting for the right conditions to reveal itself. And those conditions are influenced by the weather, by the materials involved, by the very humidity of the air. On a dry winter day, static shocks are more common because dry air is a better insulator. There is less moisture in the air to carry charge away, so the charge builds up on your body and waits for a more dramatic release. On a humid summer day, the moisture in the air helps conduct charge away more gradually, so you rarely get a sharp spark. This is all one piece of a larger picture. The rules that govern the spark from your finger are the same rules that govern the lightning bolt. Lightning is static electricity, but on a scale so enormous that it is hard to hold in the mind. Inside a storm cloud, particles of ice and water move and collide, driven by strong winds and updrafts. These collisions, much like the rubbing of a sock on a carpet, transfer electrons from one set of particles to another. Over time, the cloud develops regions of positive and negative charge. Typically, the bottom of the cloud becomes negatively charged, while the top becomes positively charged. The negative charge at the bottom of the cloud repels electrons in the ground beneath it, pushing them away and leaving the ground with a net positive charge. The cloud and the ground become a giant, separated pair of opposite charges, a vast electrical imbalance stretched across the sky. The air between the cloud and the ground is normally an insulator, a blocker of electrical flow. But as the charge builds, the electrical pressure, the voltage, grows and grows. Eventually, the pressure becomes so great that the air can no longer hold the charges apart. A channel of ionized air, a conductive path, forms between the cloud and the ground, and through that channel, a massive pulse of current flows. That is the lightning bolt. It is a spark, the same as the spark from your finger, but carrying vastly more energy, spanning miles of open sky, heating the air around it to temperatures hotter than the surface of the sun for a tiny fraction of a second. The thunder that follows is the sound of that superheated air, expanding and then collapsing, a shock wave that rolls across the landscape. Lightning is a reminder that the forces we are talking about are not small or gentle by nature. They can be enormous. They can be destructive. But they operate by the same patient logic as the balloon on the wall. A buildup of charge, a difference in electrical pressure, a sudden equalization. And then, for a moment, the balance is restored, until the clouds churn again, and the process begins anew. All of this, the spark, the balloon, the lightning bolt, is the same kind of electricity. It is static electricity, charge that builds up and then discharges in a burst. It is not the steady, controlled flow that comes from a battery or a wall outlet. In a battery, the flow is continuous, a gentle drift of electrons through a wire, governed and directed. In a wall outlet, the flow is not only continuous, but rhythmic, pulsing back and forth in a steady pattern. We will come to those forms of electricity later in our walk. For now, what matters is that the underlying force is the same, the push and the pull between positive and negative charges, the tendency of the universe to seek balance, the movement of electrons from a place where they are crowded to a place where they are scarce. It is worth pausing here to let that idea settle. The spark you feel on a dry winter day and the glow of a lamp in your living room are, at the deepest level, the same thing. They are both manifestations of charge in motion. The difference is not in the nature of the electricity itself, but in how it is produced and how it is controlled. Static electricity is wild, ungoverned, sudden. Household electricity is tamed, directed, made to flow in predictable paths at predictable rates. But the electrons themselves do not know the difference. An electron is an electron. It moves where the push takes it, whether that push comes from the friction of a sock on a carpet or from the spinning of a generator in a power plant miles away. This is one of the quiet comforts of understanding electricity. It is not a collection of different, unrelated phenomena. It is one thing, one single set of principles, appearing in many different forms. Once you see the connection between the spark and the light bulb, the world begins to feel a little more coherent, a little more unified. The same rules apply everywhere. The same quiet logic runs through the whole of it. There is no need to memorize separate explanations for separate effects. There is only the push and the pull, the build-up and the flow, the charge seeking balance in its patient, eternal way. As you lie here in the dark, you might feel the faintest trace of static electricity somewhere near you. perhaps a blanket that clings slightly to your arm, perhaps a faint crackle when you shift your position. These small signals are the voice of the same force that lights up the night sky in a thunderstorm. They are the gentlest possible introduction to a world of invisible motion, a world that hums quietly all around us, beneath the threshold of ordinary attention. And they are a reminder that you are yourself an electrical creature, made of atoms, full of charge, balanced and rebalanced with every breath you take. That thought, too, can settle into the quiet of the room, blending with the slow rhythm of your own body at rest. The next step in our walk will take us from the sudden, wild movement of static charge to the materials that make controlled movement possible. Some materials welcome the flow of electrons, offering an easy path. Others resist it, holding their electrons tight. This difference between materials that allow movement and materials that do not is what allows us to build wires and circuits and all the quiet infrastructure of the electrified world. But that is for later. For now, let the image of the spark linger, soft and small, a tiny bolt of lightning in a darkened room, a brief and gentle reminder that the universe is always seeking balance. And you are part of that universe, breathing quietly in the dark, settling into your own slow return to rest. The spark fades. The tiny bolt of static discharge has done its work, and the balance is restored. The room is quiet again, and you are still here, still breathing softly in the dark, still drifting at the edge of sleep. And now we take the next step, a step that moves us from the sudden, uncontrolled leap of static electricity to something more ordered, more deliberate. To make electricity useful, to make it do work for us in a steady and predictable way, we need to be able to guide it. We need to build pathways for it to travel along, and that means we need to understand something very simple, but very important. Not all materials are the same when it comes to electricity. Some materials welcome the movement of charge, others resist it. This difference is what allows us to build the physical highway that electricity travels along, the wires and cables and connections that form the circulatory system of the modern world. Let us begin with the materials that welcome movement. These are materials in which the outermost electrons, the ones farthest from the nucleus, are held very loosely. They are not tightly bound to any particular atom. Instead, they drift easily from one atom to the next, forming a kind of shared cloud of electrons that can move through the material with very little resistance. When an electrical push, a voltage, is applied across such a material, these loose electrons respond. They begin to drift in a particular direction, moving from the negative side toward the positive side, and that drift is what we call an electric current. The material itself does not change in any permanent way. The atoms stay where they are. Only the electrons move, gliding through the spaces between the atoms like water flowing through a bed of smooth stones. Materials that allow this easy movement of electrons are called conductors. The word conductor simply means something that carries or conveys something else. A conductor of music leads an orchestra. A conductor of heat allows warmth to pass through it. And an electrical conductor is a material that allows charge to move through it with very little hindrance. The most common conductors, and the ones we rely on for almost all of our electrical wiring, are metals. Copper is the most widely used. It is relatively abundant, relatively easy to shape into wires, and it conducts electricity very well. Its atoms are arranged in a regular, repeating pattern, a crystal lattice, and each copper atom contributes one or two of its outermost electrons to a shared pool that flows freely through the lattice. When a push is applied, those pooled electrons begin to drift, and current flows. Other metals are also good conductors. Aluminum is used in many long-distance power lines because it is lighter than copper, though it is not quite as good a conductor. Silver is actually a slightly better conductor than copper, but it is far too expensive to use in ordinary wiring. Gold is used in some specialized applications, especially in connectors and circuit boards, because it does not corrode or tarnish the way copper does. But for the wires in your walls, the cables that run under the streets, the cords that connect your appliances to the outlets, copper is the workhorse. It is the standard against which other conductors are measured. The key idea here, the quiet fact that makes all of this possible, is that conductors have what we might think of as loose outer electrons. The electrons are not locked in place. They are free to move, to drift, to migrate through the material in response to the gentlest of pushes. This is a remarkable thing when you stop to think about it. A solid piece of metal, something that feels hard and fixed and permanent, is actually full of tiny charged particles in constant motion, ready to flow at a moment's notice. The solidity is an illusion, or at least a partial one. The atoms themselves are fixed in their positions, vibrating gently with thermal energy, but their outermost electrons are a mobile sea, a fluid of negative charge that can be set in motion by the application of a voltage. Now let us turn to the opposite kind of material. If conductors are materials that allow electrons to move easily, there must also be materials that do not. These are materials in which the electrons are held much more tightly to their atoms. There is no shared cloud of mobile electrons. Every electron stays close to its own nucleus, bound by the attractive force of the positive protons in the center. When a voltage is applied across such a material, very little happens. The electrons may shift slightly in their positions, but they do not leave their atoms. They do not flow. The material blocks the movement of charge. These materials are called insulators. Common insulators include rubber, glass, plastic, ceramic, dry wood, and air itself, at least when the air is dry and the voltage is not too high. These materials are just as important to the electrical world as conductors are, perhaps even more important in some ways. A conductor gives electricity a path to follow. An insulator keeps it on that path. An insulator acts as a barrier, a wall, a boundary that the electrons cannot easily cross. This is why electrical wires are always coated in a layer of insulation, usually rubber or plastic. The copper wire inside is the conductor, the highway for electrons. The plastic coating on the outside is the insulator, the guardrail that keeps the electrons from spilling out, from taking a shortcut to somewhere they are not supposed to go. If you look at an ordinary lamp cord or the charging cable for your phone, you will see this arrangement. The metal conductor hidden inside and the flexible plastic jacket surrounding it, keeping the current where it belongs. The importance of insulators cannot be overstated. Without them, it would be almost impossible to use electricity safely. Every wire would be a shock hazard. Every metal surface would be a potential path to ground. The controlled flow of charge through the circuits of a building depends on a careful arrangement of conductors and insulators working together. The conductors carry the current where it needs to go. The insulators keep it from going anywhere else. This is a partnership, a quiet collaboration between two kinds of materials with opposite electrical personalities. There is a calm, steady logic to this. The world is made of materials, and those materials differ in how they treat the electron. Some are generous, letting electrons move freely. Some are strict, holding electrons tight. And by choosing the right material for the right job, we can build pathways for electricity, safe and predictable routes that electrons can follow, from a source of push to a device that uses their energy, and back again. This is the foundation of wiring, of circuitry, of every electrical system ever built. Let us pause for a moment and think about something you may have noticed if you have ever looked up at a power line on a quiet afternoon. A bird sits on the wire, perfectly content, perfectly safe. The wire is bare metal, uninsulated, carrying a very high voltage, often thousands of volts. And yet the bird feels nothing. It does not get a shock. It does not even seem to notice the electricity flowing just beneath its feet. This seems puzzling at first, but it makes perfect sense once you understand the roles of conductors and insulators, and the idea of a complete path. Electricity needs a complete loop, a circuit, to flow. It does not simply flow into any object that touches a wire. It flows only if that object provides a path to a place with a different electrical pressure. The bird, sitting on a single wire, has both feet at the same voltage. There is no difference in electrical pressure between its 2 feet. The wire is a good conductor. so the current flows easily through the wire itself. The bird's body is a relatively poor conductor compared to the copper or aluminum of the wire. The current has no reason to detour through the bird. The easier path, the path of least resistance, is straight along the wire. So the bird sits, undisturbed, a small living reminder that electricity is not a malicious force that leaps out at anything that comes near it. It follows rules. It follows the path of least resistance. And if that path does not include a particular creature, the creature remains safe. The same principle applies to the insulation on a wire. The plastic coating does not conduct electricity. It is an insulator. If you touch a properly insulated wire, even if current is flowing inside it, you will not feel a shock. The insulator blocks the path. Your body does not become part of the circuit. The electrons continue on their way inside the copper, and your hand remains separate, insulated, safe. This is why it is so important that insulation remains intact. A frayed cord, a cracked plug, a wire with the plastic worn away. These are hazards because they expose the conductor, and they create the possibility that a stray finger or a metal surface might complete a circuit in an unintended way. Air itself, as we noted, is normally an insulator. This is why electricity does not simply arc from the wires in your walls to every object in the room. The air holds the charge back, keeps it contained within the conductors. But air has its limits. If the voltage becomes high enough, the air can break down, ionize, and become a conductor for a brief moment. That is what happens in a lightning strike, and it is also what happens in the tiny spark of static discharge. The voltage overcomes the insulating properties of the air, and a current flows. For the relatively low voltages found in a home, around 120 or 230 volts, the air is a perfectly adequate insulator. The thickness of a layer of rubber or plastic around a wire is more than enough to keep the current contained. There is a quiet elegance to all of this. The world provides us with materials that conduct and materials that insulate. We take these materials and arrange them carefully, building pathways of metal and barriers of plastic, creating a controlled environment in which electrons can be made to flow exactly where we want them to go, and nowhere else. The lamp on your bedside table is a small example of this arrangement. Inside the cord, a copper wire, a conductor. Around the copper, a jacket of plastic, an insulator. Inside the lamp itself, more wire, more insulation, and a bulb socket made of metal and ceramic. Conductor and insulator working together. The electricity flows from the wall, through the cord, into the bulb, and back out again, all within the safe confines of its designated pathway. It never touches your hand. It never escapes into the room. It just does its quiet work, and the light glows, and the room is a little less dark. This partnership between conductor and insulator is one of the oldest and most settled ideas in the whole field of electricity. It was understood, in practical terms, long before anyone knew exactly what an electron was. Early experimenters with electricity learned very quickly that some materials would carry the mysterious force, and others would block it. They learned to wrap their wires in silk or gutta percha, a natural rubber-like material from trees. They learned to use glass insulators on telegraph poles, separating the live wire from the wooden pole and the ground. These were empirical discoveries, made by trial and error, but they were built on the same underlying reality that we now describe with words like electron and atom and charge. The materials have not changed, the rules have not changed, only our understanding has deepened. And so, as you lie here in the dark, you are surrounded by this quiet architecture. In the walls around you, copper wires run through plastic sheathing. In the devices near you, tiny traces of metal are laid down on insulating boards of fiberglass or ceramic. The whole room is a landscape of conductors and insulators, carefully arranged, quietly doing their jobs. The electricity that flows through that landscape is silent and invisible, but it is not uncontrolled. It is guided. It is contained. It follows the paths we have built for it, because the materials we have chosen make those paths the easiest ones available. The conductor invites, the insulator forbids, and together they make the modern world possible. Let this thought settle gently, like a leaf coming to rest on still water. The same force that leaps wildly from a cloud to the ground in a lightning bolt is, in your home, calm and contained, flowing through channels of metal, held back by barriers of plastic and rubber. It is the same force, the same electrons, the same push and pull between positive and negative. The only difference is the arrangement of materials, the careful choice of conductor and insulator, the patient human work of building safe pathways for an ancient, natural energy to travel along. And as you drift closer to sleep, those pathways hum softly around you, silent and steady, carrying the quiet pulse of the electrified world through the dark. The quiet pulse continues, steady and unseen, flowing through the pathways we have built for it. But up until now, we have been speaking mostly about what electricity is and where it can travel. We have not yet talked about what makes it move in the first place. A conductor, a copper wire, is like an empty pipe waiting for water. The pipe itself does not make the water flow. Something else must provide the push. Something must create a difference, an imbalance, a reason for the water to move from one place to another. The same is true for electricity. The electrons in a wire will not move on their own. They need a push, and that push has a name, a very simple name, once we understand what it actually describes. Think about water for a moment. If you have a tank of water sitting on a hill and a pipe running down to a lower field, the water will flow through the pipe. It will flow because there is a difference in height between the tank and the field. Gravity pulls the water down, and the difference in height creates pressure. The greater the difference in height, the greater the pressure, and the more forcefully the water will flow. If the tank and the field were at the same level, the water would sit still. There would be no pressure, no push, no reason for the water to move. The difference in height is what makes the flow possible. Electricity works in a very similar way, except the difference is not in height. It is a difference in electrical charge, a difference in the balance of positive and negative between 2 points. When one point has an excess of electrons compared to another point, there is an electrical pressure between them. The electrons want to move from the place where they are crowded to the place where they are scarce. They want to restore balance. This electrical pressure, this difference in charge between 2 points, is what provides the push. It is what makes electrons flow through a conductor, and this push is called voltage. The word voltage may sound technical, but the idea behind it is as simple as the idea of water pressure. Voltage is not a substance. It is not a thing you can hold in your hand. It is a measure of how strong the push is, how much pressure exists between 2 points in an electrical system. It is named after an Italian scientist named Alessandro Volta, who lived in the late 1700s and early 1800s, and who invented one of the first reliable sources of steady electrical push, the voltaic pile, which was an early form of battery. But the name is just a label. The concept itself is older than the name, as old as the first spark that ever jumped between 2 charged objects. Voltage is measured in units called volts. The volt is simply the standard unit of electrical pressure, just as the pound or the kilogram is a standard unit of weight. When we say that a battery provides 1.5 volts, we mean that the difference in electrical pressure between the 2 ends of that battery is 1.5 volts. One end has an excess of electrons relative to the other. Connect a wire between the 2 ends, and the electrons will flow from the negative end to the positive end, driven by that pressure difference. Disconnect the wire, and the pressure remains, waiting, but no current flows because the path is broken. Different sources of electricity provide different amounts of voltage. A small battery, the kind you might put in a remote control or a wall clock, typically provides about 1.5 volts. That is a very gentle push. It is enough to move electrons through the small circuits of a clock or a television remote, but it would not be nearly enough to power a lamp or a toaster. A car battery provides about 12 volts. That is a stronger push, enough to turn a starter motor and fire the spark plugs in an engine. A wall outlet, in places like the United States, provides around 120 volts. In much of Europe and many other parts of the world, the standard wall outlet provides around 230 volts. These are stronger pushes still, enough to run washing machines and heaters and all the other appliances of a modern home. And on the power lines that cross the countryside, the voltage can be hundreds of thousands of volts, a push so strong that it can send electricity across entire states and provinces with acceptable losses along the way. But here is the important thing to remember. Higher voltage does not mean a different kind of electricity. It simply means a stronger push. The electrons themselves are the same. The conductors they move through are the same. The only difference is how forcefully they are being driven. A gentle stream and a rushing river are both water. A soft breeze and a gale-force wind are both air. A battery at 1.5 volts and a transmission line at 500,000 volts are both electricity, the same fundamental force, differing only in the magnitude of the pressure. This is a comforting thought, in its own quiet way. The universe does not multiply mysteries unnecessarily. It uses the same rules at every scale. The push that drives a wristwatch and the push that drives a city are the same kind of push. The only thing that changes is the size of the difference, the strength of the pressure. Once you understand voltage as a simple difference, a simple pressure, you understand a great deal. You understand why a battery has two ends, one marked positive and one marked negative. You understand why a wall outlet has two slots, one carrying the push and the other providing the return path. You understand why birds can sit on a high-voltage wire and feel nothing, because both of their feet are at the same voltage, and without a difference in pressure, there is no push to drive current through their bodies. Voltage is sometimes called electromotive force, a phrase that means exactly what it sounds like. The force that moves electricity, the pressure that pushes electrons through a conductor. But voltage alone is not the whole story. Voltage is the potential for movement. It is the difference waiting to be resolved. Without a complete path, without a circuit, voltage just sits there. It is a quiet promise of flow, not the flow itself. A battery sitting on a shelf has voltage between its terminals. The push is there, ready and waiting. But because there is no wire connecting the two ends, no current flows. The pressure is present, but it is not doing any work. It is potential energy, stored and still. We can think of it like a book sitting on a high shelf. The book has potential energy because of its height. If it falls, that potential energy will be converted into motion, into kinetic energy. But as long as it sits on the shelf, the potential is just potential. It is a difference in height waiting to be used. Voltage is a difference in electrical pressure waiting to be used. The moment we connect a conductor between the two ends of the battery, the potential is released. The electrons begin to move. The pressure finds a path to equalize, and current begins to flow. This brings us to a gentle distinction that is worth holding in the mind, even if only loosely. Voltage is the push. Current is the flow. They are related, but they are not the same thing. You can have voltage without current, as in a battery that is not connected to anything. You cannot have current without voltage, because without a push, the electrons have no reason to move. The two ideas go together, like the pressure in a water pipe and the actual movement of water through that pipe. High pressure can exist without flow if the valve is closed, but when the valve opens, the pressure drives the water through, and the flow begins. This relationship between push and flow will become clearer as we continue our walk. In the next part of our journey, we will look more closely at current itself, at the actual movement of electrons through a conductor, and at the way that movement is measured and described. But for now, let the idea of voltage settle into your mind, like a stone dropping gently into still water. Voltage is a push. Voltage is a difference in electrical pressure between 2 points. It is what makes electricity move. It is not a mysterious substance or an abstract concept. It is a simple, measurable, understandable thing, as real as the pressure in a garden hose, as real as the weight of water behind a dam. And here is another small, quiet thought to carry with you into sleep. Your own body runs on voltage. The signals that travel along your nerves, the tiny electrical impulses that tell your heart to beat, and your lungs to breathe, and your eyelids to grow heavy with the approach of rest. Those signals are driven by voltage differences across the membranes of your cells. The voltages are tiny, measured in thousandths of a volt, but they are voltages nonetheless. The same push that lights a city also flickers inside you, quiet and steady, keeping the rhythm of your life. You are an electrical creature, made of atoms and charge and the gentle pressure of difference, seeking balance just like everything else in the universe. And as you sink deeper into the soft surface beneath you, that internal voltage continues its quiet work, asking nothing of your conscious mind, maintaining its patient rhythm in the dark. The push is always there. The potential is always present. Whether it is the 1.5 volts of a small battery in a drawer, the 120 or 230 volts in the walls around you, or the tiny, life-sustaining voltages that move through your own nerves, the idea is the same: a difference, a pressure, a quiet invitation to move. And when the path is complete, when the circuit is closed, that invitation is accepted, and the flow begins. But the flow is a story for another part of the night, another step on this slow and gentle walk. For now, just the push, just the quiet, patient pressure, waiting for its moment, holding the promise of movement in the dark. The promise of movement, the quiet, patient pressure waiting in the dark. Now we turn to what happens when that invitation is accepted, when the path is complete and the circuit is closed. The push is applied, the difference in electrical pressure is present, and the electrons begin to move. They drift through the conductor, slowly and steadily, like a vast, gentle migration of tiny particles, each one nudging the next, a collective movement that is almost impossibly slow on an individual level, but that propagates its effect at a speed approaching the speed of light. This movement, this actual flow of charge through a material, is called current. Current is not the push. Current is the result of the push. It is the thing that happens when voltage is applied across a conductor. The electrons, those loosely held outer particles in the atoms of the metal, feel the pressure difference and begin to drift from the negative side toward the positive side. They do not move in a straight line. They jostle and bounce, ricocheting off the atoms of the conductor, taking a meandering, zigzag path through the material. But their overall direction, their net drift, is toward the positive. And that drift is what we mean when we say that an electric current is flowing. Current is measured in a unit called the ampere, named after a French scientist named André-Marie Ampère, who lived from 1775 to 1836, and who did foundational work in understanding the relationship between electricity and magnetism. In everyday speech, the word ampere is often shortened to amp. When someone says that a circuit carries 10 amps, they mean that a certain amount of charge is moving past a given point in the wire each second. The ampere is a measure of flow rate, the electrical equivalent of how many gallons of water pass through a pipe every minute. It tells you how much electricity is moving, just as a flow meter on a water pipe tells you how much water is moving. Let us return to our water comparison, because it continues to be a helpful way to hold these ideas in the mind. Imagine a pipe connected to a water tank. The height of the tank creates pressure. That pressure is like voltage. When you open a valve at the bottom of the pipe, water begins to flow. The amount of water that comes out each second, the volume of flow, is like current. You can have high pressure with very little flow, if the pipe is very narrow or the valve is barely open. You can have low pressure with a great deal of flow, if the pipe is very wide and the valve is fully open. Pressure and flow are related, but they are not the same thing. Voltage and current are related, but they are not the same thing. This distinction is important, and it is worth spending a little time with, because it helps clear away a common confusion. People often think of voltage as the dangerous part of electricity, because high voltage signs are everywhere, on fences and substations and the backs of appliances. But voltage alone, without current, does no harm. A static shock from a doorknob can involve thousands of volts, but the total amount of charge that moves is so tiny that the current lasts for only the briefest instant, and it does not injure you. What makes electricity dangerous to the body, and what makes it useful in an appliance, is current. Current is the actual movement of charge through a material, whether that material is a copper wire or a human body. It is current that heats the filament in a light bulb. It is current that turns the motor in a fan. And it is current, passing through the heart or the nervous system, that can disrupt the body's own delicate electrical rhythms. A very small current, just a few thousandths of an amp, passing through the human body, can be felt as a mild, tingling sensation. A current of around 10 to 20 thousandths of an amp can cause muscles to contract involuntarily, making it difficult to let go of the source of the current. Currents above about 1/10 of an amp can be lethal, especially if they pass through the chest and interfere with the heart's natural pacing signals. These numbers are not meant to frighten. They are simply the physical facts, as settled and well understood as the fact that water can drown. The point is that current is the active agent. Current is what does the work, for good or for ill. Voltage is just the push that makes current possible. In a household circuit, the current drawn by an appliance depends on what the appliance needs to do its work. A small LED light bulb might draw only a few tenths of an amp. A toaster or a space heater might draw 10 or 12 amps. A large air conditioner might draw 20 amps or more. The voltage at the wall outlet stays roughly the same, 120 volts or 230 volts depending on where you live. But the current varies according to the appliance. The outlet provides the pressure. The appliance determines how much flow that pressure produces, based on its own internal characteristics, which we will talk about in the next part of our walk. Current is sometimes described in terms of the number of electrons passing a point in a given time. 1 amp of current corresponds to about 6 quintillion electrons passing a point each second. That number is so large, it is hard to hold in the mind. 6 quintillion is a 6 followed by 18 zeros. It is a number that belongs to the realm of atoms and electrons, a realm where quantities are either unimaginably vast or unimaginably tiny, with very little middle ground. The important thing is not the exact number, but the idea that current is a rate. It is a measure of how much charge is moving, how many electrons are drifting past, how heavy the electrical traffic is on the conductor. The electrons themselves move surprisingly slowly. This is one of those quiet facts that can feel counterintuitive, but it is true. When you flip a light switch, the light comes on almost instantly. You might assume that the electrons from the switch zoom through the wire at incredible speed to reach the bulb. But the actual drift velocity of electrons in a typical household circuit is on the order of a few centimeters per minute. That is slower than a snail. The reason the light comes on so quickly is that the wire is already full of electrons, like a pipe already full of water. When you push on one end, the push propagates through the entire pipe almost instantly, and water comes out the other end almost immediately. The individual water molecules do not travel the length of the pipe in that instant. They just nudge their neighbors, and the nudge travels fast. The same is true in a wire. The electric field that drives the electrons propagates at close to the speed of light, but the electrons themselves drift along at a leisurely pace, bumping and wandering through the atomic lattice. This image is worth holding on to as you drift towards sleep. A vast crowd of electrons, jostling and shuffling through the copper, moving so slowly that you could outpace them with a gentle stroll, and yet their collective nudge, the wave of motion that passes through them, travels at nearly the speed of light. It is a quiet, almost meditative picture. The individual components moving slowly, the signal moving fast, the part and the whole, doing different things on different scales of time and speed. Current can be steady or it can vary. In a circuit powered by a battery, the current flows in one direction only. The electrons move from the negative terminal through the circuit and back to the positive terminal. This is called direct current, and we will spend more time with it later. In a circuit powered by a wall outlet, the current changes direction many times each second, flowing first one way, then the other, in a smooth, rhythmic pattern. This is called alternating current, and we will also spend more time with it later. But whether steady or alternating, the basic idea is the same. Current is the flow of charge. It is the response to voltage. It is the movement that happens when the push is applied and the path is complete. The relationship between voltage and current is one of the most fundamental relationships in all of electricity. For a given circuit, the amount of current that flows depends on the amount of voltage applied and on something else, a property of the circuit that opposes the flow. That property is called resistance, and it is the subject of the next part of our walk. But even before we name it and describe it, we can feel its presence in the water analogy. A wide, smooth pipe allows a lot of water to flow, even with modest pressure. A narrow, rough pipe restricts the flow, even with high pressure. Electrical circuits have the same kind of variation. Some circuits allow a lot of current to flow with a small voltage. Others restrict the current, requiring a larger voltage to achieve the same flow. This three-way relationship between push, flow, and resistance was first expressed clearly by a German physicist named Georg Ohm in the early 1800s. He found that for many materials, the current through a conductor is directly proportional to the voltage applied across it. Double the voltage and you double the current, as long as the resistance stays the same. This relationship is known as Ohm's law, and it is one of the quiet pillars on which the entire field of electrical engineering rests. But it is not necessary to remember the law or the name. What matters is the intuition, the simple, almost physical sense that a stronger push produces a stronger flow, and that the nature of the path determines how much flow you get for a given push. Think of a garden hose. The pressure comes from the tap or the pump. The flow is the water streaming out the end. If you kink the hose, you increase the resistance, and the flow drops, even though the pressure stays the same. If you unkink the hose, the resistance drops, and the flow increases. If you open the tap wider, you increase the pressure, and the flow increases, as long as the hose stays the same. These are simple, everyday experiences, and they map directly onto the behavior of electrical circuits. Voltage is the pressure, current is the flow, resistance is the kink in the hose, the narrow section, the roughness of the pipe's interior. It is a physical intuition grounded in the ordinary world of water and pipes and valves, and it will serve you well. As you lie here, letting these words drift through your mind, you might think about the current flowing in the walls around you. In the wires that run behind the plaster and the paint, electrons are shuffling along, a slow, steady drift of negative charge, nudged by the voltage from the outlet. They move in one direction, then reverse again, 60 times every second if you are in the United States, 50 times every second if you are in much of Europe. This rhythmic back and forth is the heartbeat of the electrified world, a pulse that never stops, a quiet tide of charge that ebbs and flows in the dark while the rest of the world sleeps. It is always there. It has been there for decades, ever since the wires were first run through these walls. It is one of the constant background facts of modern life, so constant that we rarely think about it at all. But it is real. It is physical. It is electrons, actual tiny particles of matter, moving in response to a pressure difference, doing work, generating heat, spinning motors, glowing lights, keeping the quiet machinery of the household turning through the night. And you are part of this same world of flow. Your own nervous system uses currents, tiny ones, measured in millionths of an amp, to send signals from your brain to your body and back again. The current that tells your heart to beat, the current that tells your lungs to expand, the current that tells your eyelids to grow heavy and your thoughts to slow, and your body to sink into the soft embrace of rest. All of this is the same kind of thing as the current in the wires. A flow of charge. A movement of ions rather than free electrons, in the case of the body, but the same basic principle, a difference in pressure, a path, a flow, a settling toward balance. Let that thought settle with you. The current flows. It flows in the wires. It flows in your nerves. It flows in the lightning bolt and in the tiny spark from your finger. It is all the same quiet force, the same patient movement of charge, seeking balance, doing work, lighting the dark. And as you drift further into the soft edges of sleep, the current continues its gentle, rhythmic pulse, inside you and around you, steady as a tide, quiet as a breath, carrying you slowly toward rest. The current flows, steady and quiet, but it does not flow without effort. Nothing in the physical world moves without some kind of opposition, some kind of friction, some gentle pushback from the material it moves through. A boat moving through water feels the drag of the water against its hull. A person walking through tall grass feels the brush of the blades against their legs. And electrons moving through a conductor feel a kind of drag as well. They bump into the atoms of the material. They jostle and scatter and lose a little of their forward momentum with each collision. This opposition, this pushback from the material, is what we call resistance. Resistance is a simple idea, and the word itself is a good plain description of what it does. It resists, it pushes back, it makes it harder for current to flow. Every material has some amount of resistance, even the best conductors. Copper is an excellent conductor, but it is not perfect. When electrons drift through a copper wire, they still bump into copper atoms. They still lose a little energy with each bump. The wire still pushes back, just a little. Other materials push back a great deal. Insulators like rubber or glass have such high resistance that, for all practical purposes, no current can flow through them at ordinary voltages. The electrons are held too tightly. The resistance is enormous. And so the current, if any, is vanishingly small. Resistance is measured in a unit called the ohm, named after the same Georg Ohm we mentioned earlier, the German physicist who first described the relationship between voltage, current, and resistance in a clear mathematical way. The symbol for ohms is the Greek letter omega, which looks like a small horseshoe, but we will not use symbols here. We will simply say ohms, a word that sounds soft and round, like a quiet note held in the dark. A material with a resistance of 1 ohm will allow 1 amp of current to flow when 1 volt of pressure is applied across it. Double the resistance to 2 ohms, and the same 1 volt will push only half an amp through. Double the voltage to 2 volts across that same 1 ohm, and the current doubles to 2 amps. This is the simple, proportional relationship that Ohm described, and it holds true for many materials under many conditions. But we do not need to do any math. The numbers are just there to show the relationship. The important thing is the idea, the feel of it. Resistance is the narrow section of pipe. Resistance is the rough, bumpy interior of an old water main. Resistance is the kink in the garden hose. It is anything that makes it harder for the flow to continue. And because it makes the flow harder, it takes some of the push, some of the voltage to overcome it. That push does not disappear. It is converted into another form of energy. In almost all cases, that other form is heat. This is one of the most important and most familiar consequences of resistance. When current flows through a material that has resistance, the material warms up. The electrons bump into the atoms, and each bump transfers a tiny amount of kinetic energy, the energy of motion, into the atoms themselves. The atoms vibrate a little more vigorously. The temperature of the material rises. This is exactly how a toaster works. The wires inside a toaster are made of a special alloy, a mix of metals, that has a relatively high resistance. When current is pushed through those wires, they heat up until they glow a warm orange red. The heat radiating from those glowing wires is what browns the bread. The same principle is at work in an incandescent light bulb. The filament inside the bulb is a thin wire, usually made of tungsten, a metal that can withstand very high temperatures without melting. The filament has enough resistance that when current flows through it, it heats up to several thousand degrees, and it glows white hot, producing light. In this case, the heat is so intense that a significant portion of the energy is released as visible light. But heat is also the reason that electrical devices can feel warm to the touch after they have been running for a while. The charger for your phone, the power supply for your computer, the motor in a fan, all of these things contain wires and components that have resistance. As current flows through them, they warm up. This is normally not a problem. The devices are designed to handle the heat, to dissipate it into the surrounding air, to keep their internal temperatures within safe limits. But it is a reminder that resistance is always present, always doing its quiet work, always converting a little bit of the electrical push into warmth. This heating effect can be seen as a kind of loss, and in many contexts it is. When electricity travels hundreds of miles from a power plant to a city, some of the energy is lost as heat in the transmission wires. Engineers work very hard to minimize these losses by using materials with low resistance like copper and aluminum, and by using high voltages which allow the same amount of power to be delivered with less current, and therefore less heating. We will talk more about that when we discuss the long trip electricity takes to reach your home. But resistance is not always a problem to be solved. Sometimes it is the whole point. A toaster without resistance would not heat up. An incandescent bulb without resistance would not glow. An electric blanket, the kind you might be lying under right now, uses resistance wires to produce a gentle, even warmth. The resistance is designed deliberately, to convert electrical energy into heat in a controlled and useful way. Everyday electrical appliances are designed with a specific amount of resistance in mind. A light bulb, a toaster, a hair dryer, each of these things presents a certain resistance to the circuit. That resistance, combined with the voltage of the outlet, determines how much current will flow. A high-resistance device draws very little current. A low-resistance device draws a lot of current. If the resistance is too low, the current can become very high, and the wires can heat up beyond safe limits. This is what happens in a short circuit, when the normal path of current is bypassed, and the electricity finds an unintended, very low-resistance route back to the source. The current surges, the wires heat rapidly, and a fire can start if the circuit is not protected by a fuse or a breaker. A fuse is a simple, quiet safety device. It is a thin piece of wire designed to melt if the current exceeds a certain level. When it melts, the circuit is broken and the current stops flowing. A circuit breaker does the same job, but it uses a mechanical switch that trips when the current gets too high, and it can be reset rather than replaced. Both devices are guardians of the circuit, watching over the flow of current, ready to interrupt it if the resistance drops too low and the current climbs too high. They are part of the quiet infrastructure of every electrified building, sitting in their panels, rarely thought about, doing their patient work year after year. Resistance depends on several factors. The material itself is the most important. Copper has low resistance. Aluminum has slightly higher resistance but is lighter and cheaper. Silver has the lowest resistance of any common metal, but it is expensive. Tungsten has higher resistance and a very high melting point, which makes it useful for light bulb filaments. Nichrome, an alloy of nickel and chromium, has high resistance and excellent heat tolerance, which makes it ideal for toasters and hair dryers and electric ovens. The length of the conductor also matters. A longer wire has more resistance than a shorter wire of the same material and thickness, just as a longer hallway takes more effort to walk down. The thickness of the conductor matters as well. A thicker wire has less resistance than a thinner wire, just as a wide pipe allows water to flow more easily than a narrow one. And temperature matters too. In most materials, resistance increases as temperature rises. The atoms vibrate more vigorously, making it harder for electrons to pass through without colliding. All of these factors are well understood. They are part of the settled, established knowledge of electricity, the kind of knowledge that engineers use every day to design circuits and build devices. There is very little mystery here, just the quiet, reliable behavior of materials under the influence of voltage and current. And yet, there is a certain beauty in that reliability. The same simple relationship, the same proportional response, holds true across an enormous range of scales, from the tiny currents in a microchip to the massive currents in a transmission line. Resistance is a property of the material world, as fundamental as mass or density, and it operates with the same calm, impersonal consistency. Think for a moment about the wires in the walls around you. They are copper, a good conductor, with low resistance. They are thick enough to carry the expected current without heating up too much. They are insulated with plastic, a material with extremely high resistance, so high that at ordinary voltages, no measurable current flows through it. The current moves through the copper, resisted only slightly, and the insulation keeps it from straying. And somewhere in the circuit, perhaps in the basement or a utility closet, there is a panel of breakers or fuses, each one watching over a different loop, ready to open the circuit if the resistance drops and the current rises beyond safe levels. All of this is resistance at work. Resistance as a design tool, resistance as a safety consideration, resistance as a fundamental part of the electrical world. As you lie here, letting these words drift past you, you might notice the faint warmth of the device you are listening on, or the subtle heat of a nearby lamp, or the cozy weight of an electric blanket if you have one. That warmth is resistance. It is the gentle, constant conversion of electrical push into heat. It is the electrons bumping their way through the wire, giving up a little of their energy with each collision, and passing that energy on to the atoms of the material, which vibrate a little faster, radiating their quiet warmth into the cool air of the room. It is a soft, almost comforting thought. The same process that lights a city and powers a factory is also the process that keeps your toes warm on a cold night. It is all one thing. It is all the same quiet logic. And resistance is not just a property of wires and toasters. It is a property of everything. The air you breathe has resistance, which is why lightning bolts are so enormous. The voltage must be high enough to overcome the immense resistance of miles of air. The ground beneath you has resistance, which is why grounding systems in buildings are carefully designed to ensure a low-resistance path to the earth. Your own body has resistance, which varies depending on whether your skin is dry or wet, thick or thin. The resistance of dry skin can be many thousands of ohms, which is why a brief touch to a household voltage might only produce a mild tingle. Wet skin has much lower resistance, which is why electrical safety is especially important around water. These are all manifestations of the same underlying property, the same gentle pushback that every material offers to the flow of charge. Let the idea of resistance settle into your mind like a stone settling into the bed of a stream. The water flows around it. The stone does not stop the flow, but it shapes it, redirects it, slows it just a little. Resistance shapes the flow of electricity. It determines how much current will flow for a given push. It turns some of that push into warmth. It is the reason wires are made of copper and not of rubber. It is the reason toasters glow and fuses blow. It is one of the three fundamental quantities, along with voltage and current, that describe every electrical circuit ever built. And it operates with a quiet, mathematical consistency that has been understood for nearly 200 years, a settled piece of knowledge in a world full of unsettled things. There is comfort in that. There is comfort in knowing that the wires in your walls are not mysterious or capricious. They are not doing something new or unknown. They are obeying the same rules they have always obeyed, the rules that Ohm wrote down in the early 1800s, the rules that every electrical engineer since has relied on. Resistance is predictable. It is steady. It is, in its own quiet way, a kind of friend to the half-asleep mind, a reminder that some things in the universe are settled and solid and can be relied upon to behave tomorrow exactly as they behave today. And as you drift closer to sleep, that reliability is a soft and welcome presence, a steady hum beneath the surface of thought, a quiet constant in a world of change. The steady hum continues, a quiet constant beneath the surface of thought. And now we come to an idea that ties together everything we have talked about so far. The push, the flow, the resistance, all of these things exist in relation to one another, but they need a stage on which to play out their quiet drama. They need a path, not just any path, but a complete one, a loop, a closed circle that begins and ends at the same place. Without that loop, without that completed circle, nothing moves. The push is present, the pressure is waiting, but the electrons have nowhere to go. They cannot simply flow outward and disappear. They must return. They must come home. This completed loop is called a circuit. The word circuit shares its root with the word circle. It means a going around, a journey that returns to its starting point. And that is exactly what an electrical circuit is. It is a path that starts at a source of voltage, travels out through whatever devices or components need to be powered, and then returns to that same source, completing the loop. Charge does not get used up in the process. It simply goes around and around, picking up energy from the voltage source at the beginning of the loop, delivering that energy to the devices along the way, and returning to the source depleted of energy but not of charge. The electrons themselves are not consumed. They are just carriers, little couriers of energy, picking up their package at one end and dropping it off at the other. Think again of water, our quiet companion in this journey. A water pump does not consume water. It circulates it. The pump takes water from a reservoir, pushes it through pipes to a fountain or a water wheel, and then the water returns to the reservoir to be pumped again. The water is the medium, not the fuel. The energy comes from the pump, and the water simply carries that energy to where it is needed. An electrical circuit works the same way. The battery or the generator is the pump. The wires are the pipes. The electrons are the water. And the light bulb or the motor or the speaker is the fountain, the place where the energy is released to do useful work. The electrons go around and around, a closed loop of flow, a circle of current that never stops as long as the circuit is complete and the push is present. Every circuit, no matter how simple or how complex, has three essential parts. First, there must be a source of push, a voltage source. This could be a battery, a generator, a solar panel, any device that creates a difference in electrical pressure between its two terminals. Second, there must be a path, a conductor that carries the current from the source to the device and back again. This is usually copper wire, though it can be any conductive material. And third, there must be a load, something that uses the energy. The load is the light bulb, the motor, the heating element, the speaker. It is the thing that resists the flow in a useful way, turning electrical energy into light or motion or heat or sound. Without a load, the circuit would have very low resistance, and the current would become very high, which is what we described earlier as a short circuit. The load is what makes the circuit useful rather than dangerous. These three parts, the source, the path, and the load, are present in every electrical device you have ever used. In a flashlight, the batteries are the source, the metal strips and the switch are the path, and the small light bulb is the load. When you slide the switch to the on position, you complete the circuit. You close the loop. The voltage from the batteries pushes electrons through the bulb's filament resists the flow and heats up and glows, and the electrons return to the battery. The loop is complete. The circle is closed. The light shines. When you slide the switch to the off position, you break the circuit. You open the loop. The path is interrupted, and the electrons can no longer flow. The pressure is still there, waiting at the terminals of the battery, but the road is closed. The light goes out. This is the fundamental action of every switch in every device. It is a gate, a drawbridge, a controlled break in the circuit. When the bridge is down, the traffic flows. When the bridge is up, the traffic stops. The simplicity of this idea is part of its quiet beauty. The entire electrified world, from the smallest hearing aid to the largest factory, is controlled by opening and closing circuits, by making and breaking loops, by allowing or preventing the flow of electrons through a closed path. There are two basic ways to arrange the parts of a circuit, and the difference between them matters for how the circuit behaves. The first way is to connect everything in a single loop, one after the other, like beads on a string. This is called a series circuit. In a series circuit, the current has only one path to follow. It flows through the first component, then the second, then the third, and then back to the source. Because there is only one path, the same current flows through every part of the circuit. The voltage, however, is divided among the components. Each one gets a share of the total push, proportional to its resistance. A series circuit has a particular vulnerability, a particular way of failing that many of us have experienced, perhaps without knowing the name for it. Think of the old-style string lights, the kind that were common on Christmas trees decades ago. A single strand of small bulbs, each one glowing with a warm, soft light. In those lights, the bulbs were connected in series. The current flowed through one bulb, then the next, all the way down the string, and if one bulb burned out, if its filament broke, the circuit was broken. The loop was opened, and every single bulb on the string went dark, not because they were all broken, but because the single path had been interrupted. Finding the dead bulb was a quiet, patient task, a matter of testing each one until the broken link was found and replaced. This is the defining characteristic of a series circuit. One failure breaks the loop and everything stops. The second way to arrange a circuit is to split the path into branches so that the current has multiple routes to follow. This is called a parallel circuit. In a parallel circuit, each component is connected directly to the source with its own separate path. The voltage across each branch is the same, the full voltage of the source. But the current divides among the branches, with more current flowing through the branches that have lower resistance and less through those with higher resistance. A parallel circuit is more resilient than a series circuit. If one branch fails, if one bulb burns out, the other branches are unaffected. The current still flows through them. The rest of the lights stay on. This is why modern homes are wired in parallel, not in series. Every outlet, every ceiling light, every built-in appliance is a branch off the main circuit, connected in parallel with all the others. When you turn off the lamp in the living room, the refrigerator in the kitchen does not go dark. When a light bulb burns out in the hallway, the clock radio in the bedroom keeps on humming. Each device has its own path to the source, its own private loop within the larger loop of the house. The circuit breaker or fuse that protects each branch is the quiet guardian of that arrangement, watching over the current, ready to open the circuit if something goes wrong. The parallel arrangement is so familiar, so woven into the fabric of daily life, that we rarely stop to notice it. But it is a choice, a deliberate design decision made by electricians and engineers based on a clear understanding of how series and parallel circuits behave. It is another example of the quiet, settled knowledge that underlies the electrified world. The rules are known. The behavior is predictable. A series circuit divides voltage and keeps current the same. A parallel circuit divides current and keeps voltage the same. These are not mysteries. They are facts, as solid and reliable as the fact that water flows downhill. There is a gentle rhythm to the way a circuit works. The push from the source, the flow through the path, the resistance of the load, turning some of the push into useful work. The return to the source, depleted but ready to go around again. Around and around, a quiet, invisible carousel of electrons, spinning through the wires at a leisurely drift, while the energy they carry races ahead at nearly the speed of light. It is a kind of circulation, a respiration, a breathing in and breathing out of charge. The source inhales electrons on one side and exhales them on the other, and the whole loop pulses with the steady rhythm of the push. And here is a thought that may settle gently into your mind as you drift. The circuit is not just a concept in electrical engineering. It is a pattern that appears everywhere in the natural world. The water cycle is a circuit. The ocean evaporates, the vapor rises. It condenses into clouds. It falls as rain. It flows in rivers back to the ocean. Around and around, a closed loop of water, driven by the push of the sun. The carbon cycle is a circuit. Plants take in carbon dioxide, animals eat the plants and breathe the carbon back out. The atmosphere carries it back to the plants. Around and around. The blood in your body circulates in a circuit, pumped by the heart, pushed through arteries, returning through veins, carrying oxygen and nutrients, picking up waste, coming home to be refreshed and sent out again. The circuit is a deep pattern, a fundamental shape of the universe, a way of organizing flow so that it can be sustained and directed and put to use. Your own nervous system is a circuit, or rather a vast network of circuits, billions of them, carrying tiny electrical signals from your brain to your body and back again. A thought forms, a signal travels down a nerve, a muscle contracts, a sensation returns, and the loop is closed. This is happening right now, as you lie here in the dark. Your brain is sending signals to your lungs, telling them to breathe. Your lungs are sending signals back, confirming that they have done so. Your heart is beating to an electrical rhythm set by a small cluster of cells in its upper chamber, a natural pacemaker that sends a pulse of voltage through the heart muscle 60 or 70 times a minute. A tiny circuit closing and opening, keeping the blood moving through its own closed loop. The circuit is everywhere. It is inside you. It is around you. It is the shape of how things move and return and move again. Let that shape settle into the quiet of the room, the loop, the circle, the path that returns to its starting point. The electrons in the walls around you are on their own quiet journey, pushed by the voltage from the power grid, flowing through the wires, delivering energy to the devices that hum softly in the dark, and returning to the source, over and over, a patient, tireless circulation that never stops. The switch on your lamp is a gate, a drawbridge. Right now it is open, and the circuit is broken, and the lamp is dark. But the voltage is still there, waiting at the switch, patient and ready. The moment the switch closes, the moment the bridge drops, the loop will be complete, and the light will glow, and the quiet carousel of electrons will spin once more through the filament, giving off its gentle warmth and light. There is no hurry to close that switch. The circuit can wait. The push can wait. The electrons are not impatient. They have been doing this for a very long time, and they will continue to do it long after this night has passed and the morning has come. For now, it is enough to know that the loop is there, waiting, complete in its design, ready for the moment when the path is closed and the flow begins. And that knowledge can sit with you, soft and quiet, as the night continues, and your own internal circuits, the ones that keep you breathing and your heart beating, carry on their patient work, closing and opening, a gentle rhythm in the dark. The gentle rhythm continues, the quiet opening and closing of circuits inside you and around you. And now we turn to a distinction that shapes the entire electrical world, a fork in the road that determines how electricity is generated, how it is transmitted, and how it is used. Up until now, we have talked about current as if it were one thing, a simple flow of electrons in one direction. But current does not always flow in one direction. There are two fundamentally different ways that electricity can travel, two different patterns of movement, and each one has its own strengths and weaknesses, its own history, its own place in the modern world. Let us begin with the simpler of the two. Imagine a battery connected to a light bulb, forming a closed circuit. The voltage from the battery pushes electrons in one direction. They leave the negative terminal, travel through the wire, pass through the bulb, and return to the positive terminal. They always move this way. They never reverse. The flow is steady, constant, and unidirectional, like a river that always runs downstream, never upstream. This kind of current is called direct current. In everyday speech, it is often shortened to the initials DC, said as two separate letters, D and C. Direct current is the native language of batteries. Every battery-powered device you have ever used, a flashlight, a remote control, a portable radio, a cell phone, runs on direct current. The electrons march steadily in one direction, from negative to positive, until the chemical reaction inside the battery can no longer sustain the push, and the battery runs down. Direct current is simple to understand, and it is simple to work with for small, self-contained devices. It does not require any special conversion or adaptation. The battery provides it, the device uses it, and the loop is closed. But direct current has a limitation, a quiet, practical difficulty that became apparent very early in the history of electrification. It does not travel well over long distances. To send direct current from a power plant to a city many miles away, you would need either to accept large losses of energy as heat in the transmission wires, or you would need to use very thick, very expensive cables to reduce the resistance. The reason for this is that, in a direct current system, the voltage at which the power is generated is more or less the voltage at which it must be used. You cannot easily change the voltage of direct current. You cannot step it up for efficient long-distance travel and then step it back down for safe use in homes. And without that ability, transmitting power over long distances becomes very inefficient and very costly. This limitation was not immediately obvious in the early days of electric power. The first power plants were small, serving only a few city blocks. They generated direct current at a relatively low voltage, and they sent it through thick copper cables buried under the streets. This system was championed by Thomas Edison, the famous American inventor, who built the first commercial electric power plant in New York City in 1882. It served a small area of Lower Manhattan, powering streetlights and a few wealthy customers. The system worked, but it was clear even then that it could not scale. To light up an entire city, let alone an entire countryside, a different approach was needed. That different approach was alternating current. In an alternating current system, the flow of electrons does not move steadily in one direction. Instead, it reverses direction, back and forth, many times each second. The electrons are pushed one way, then pulled back the other way, then pushed again, in a smooth, rhythmic oscillation. This back-and-forth motion is the defining characteristic of alternating current. In everyday speech, it is often shortened to the initials AC, said as two separate letters, A and C. The rhythm of this reversal is measured in cycles per second. One complete cycle, a push in one direction and a pull back in the other, is called a Hertz, named after Heinrich Hertz, a German physicist who did important early work on electromagnetic waves. In places like the United States, Canada, and a few other countries, the alternating current in wall outlets reverses direction 60 times every second, or 60 Hertz. In much of Europe, Asia, Africa, and Australia, it reverses 50 times every second, or 50 Hertz. This difference is a historical accident, the result of different standards being adopted in different parts of the world in the early days of electrification. It has no deep significance. The electricity is the same. The rhythm is just slightly different. The great advantage of alternating current, the reason it became the standard for power grids around the world, is that its voltage can be changed very easily using a device called a transformer. A transformer is a simple, elegant piece of equipment with no moving parts. It consists of two coils of wire wound around a shared iron core. When alternating current flows through one coil, it creates a changing magnetic field in the core, and that changing magnetic field induces a voltage in the other coil. By varying the number of turns of wire in each coil, the transformer can step the voltage up or down. It can take electricity at a few hundred volts and raise it to hundreds of thousands of volts for efficient long-distance transmission. Then, at the other end of the line, another transformer can bring it back down to safe levels for use in homes and businesses. This ability to change voltage at will, simply and reliably, is what made the modern power grid possible. It allowed power plants to be built far from cities, near sources of fuel or falling water. It allowed electricity to be sent across entire states and provinces, over mountains and across plains, through thin, relatively inexpensive wires. And it allowed that same electricity to be delivered to your home at a safe, usable voltage. Without alternating current, the electrified world as we know it would simply not exist. The shift from direct current to alternating current was not smooth. It was the subject of a famous dispute, sometimes called the War of the Currents, that played out in the late 1800s. On one side was Thomas Edison, who had built his business on direct current and who argued, sometimes in harsh and public ways, that alternating current was dangerous. On the other side was George Westinghouse, an industrialist who had licensed the alternating current technology developed by Nikola Tesla, a Serbian-American inventor of remarkable talent. Tesla had worked for Edison briefly, but the two men had very different temperaments and very different visions. Tesla believed in alternating current. He had designed the motors and generators that made it practical, and Westinghouse had the business sense and the resources to bring that technology to the world. The War of the Currents is a story full of drama, but we do not need to go into all of it here. What matters is the outcome. Alternating current won, not because it was intrinsically better for every purpose, but because it solved the problem of long-distance transmission in a way that direct current at the time could not. The first large-scale alternating current power plant was built at Niagara Falls in 1895, harnessing the immense power of falling water to generate electricity that was sent all the way to Buffalo, New York, more than 20 miles away. It was a triumph of engineering, and it marked the beginning of the modern electrical age. But direct current did not disappear. It simply found its own niche. Batteries produced direct current, and so direct current remained the standard for portable devices, for cars and trucks and boats, for anything that needed to store its energy and carry it along. In recent decades, direct current has experienced a quiet resurgence in new forms. Solar panels produce direct current. Computers and LED lights and many modern electronics actually run on direct current internally, even when they are plugged into an alternating current outlet. They have a small power supply, a little box, or a built-in circuit that converts the alternating current from the wall into the direct current the device needs. And very long-distance, very high-voltage direct current transmission lines have been built in some parts of the world, using modern technology that can change the voltage of direct current in ways that were impossible in Edison's time. The boundary between the two kinds of current has become softer, more permeable, as technology has advanced. Still, the fundamental distinction remains. Direct current flows one way. Alternating current flows back and forth. A battery gives you direct current. A wall outlet gives you alternating current. Most of the large motors in factories and appliances run on alternating current. Most small electronics inside their circuits run on direct current. The two kinds of current coexist, each doing what it does best, each finding its place in the larger electrical ecosystem. Let us sit for a moment with the image of alternating current, because it is a particularly soothing one for a mind that is drifting towards sleep. Imagine the electrons in the wires around you. They are not racing along at high speed. They are drifting slowly, back and forth, a gentle, rhythmic oscillation. They move a tiny distance in one direction, then stop, then move a tiny distance in the other direction, then stop, then move again, 60 times every second, or 50, depending on where you are. This is a kind of breathing, a quiet electrical respiration. The electrons do not go anywhere, in the net sense. They just sway, like water in a basin that is being gently rocked. But their sway carries energy, and that energy propagates through the circuit at nearly the speed of light, powering the devices that hum softly in the dark. This is a different picture from the one we had with direct current. Direct current is a steady march, a purposeful journey in one direction. Alternating current is a dance, a back and forth, a gentle, tireless oscillation. Both are current. Both are the movement of charge. Both can do work and produce light and generate heat, but the feel of them is different, the rhythm is different, and the choice of which one to use in any given situation is a matter of engineering, of practicality, of the quiet, accumulated wisdom of more than a century of electrical development. The fact that the whole world runs on these two kinds of current, that every electrical device you have ever used is designed for one or the other or both, is a testament to the flexibility of the underlying phenomenon. The push and the flow, the pressure and the current, the resistance and the circuit, all of these things apply equally to direct current and alternating current. The rules do not change. The physics does not care which way the electrons are moving. It only cares that they are moving, that a push is present, that a loop is closed. The distinction between DC and AC is a human distinction, a practical choice, a way of adapting the same fundamental force to different needs and different circumstances. As you lie here, drifting further into the soft edges of sleep, you might think about the tiny power supply inside the device that is playing these words. It is taking the alternating current from the wall, with its 60 or 50 back and forth cycles every second, and converting it into smooth, steady direct current for the delicate circuits inside. It is a small bridge between the two worlds, a quiet translator, doing its work without fuss or fanfare. And in the walls around you, the alternating current continues its patient oscillation, back and forth, a lullaby of electrons swaying in the dark, carrying the energy of a distant power plant into your home, into your room, into the small glowing device that speaks softly beside you as you sink deeper into rest. The energy of a distant power plant, carried by the gentle oscillation of electrons, arrives at your home so quietly that you never hear it. But that energy must come from somewhere. It must be created, generated, brought into existence from some other form of energy. Electricity is not a primary source of power in the way that coal or wind or sunlight is. It is a carrier, a way of moving energy from one place to another. And so the question naturally arises, how is it made? How do we take something like falling water or burning fuel or blowing wind and turn it into the quiet, invisible push that lights our homes and powers our devices? The answer is one of the most elegant and important ideas in all of physics, and it rests on a simple, quiet discovery that was made nearly 200 years ago. The discovery is this: if you take a wire and move it through a magnetic field, or if you take a magnet and move it near a wire, something happens inside that wire. The electrons inside the wire feel a push. They begin to move. A current begins to flow. This effect, this generation of electricity by the relative motion of a conductor and a magnet, is the basis for nearly all large-scale electrical generation in the world today. It is called electromagnetic induction, and it was first described in detail by an English scientist named Michael Faraday in the early 1830s. Faraday was a remarkable man, largely self-taught, the son of a blacksmith, who rose to become one of the most important experimental scientists of his time. He had a gift for seeing the deep patterns that connected seemingly unrelated phenomena. In his time, electricity and magnetism were known to be related in certain ways. A current flowing through a wire could deflect a compass needle. That much was known. But Faraday wondered whether the reverse might also be true. Could a magnetic field be used to create an electric current? He conducted a long series of careful, patient experiments, and in 1831 he found the answer. He wrapped 2 coils of wire around opposite sides of an iron ring. When he passed a current through one coil, creating a magnetic field, he observed a brief pulse of current in the other coil. The current appeared only at the moment the magnetic field was changing, at the moment it was switched on or off. A steady magnetic field produced nothing. A changing magnetic field produced electricity. This was the birth of electromagnetic induction. Faraday had shown that a changing magnetic field could push electrons through a wire. The practical applications of this discovery would take decades to develop, but the principle was there from the start. Move a wire near a magnet, or move a magnet near a wire, and you get electricity. The movement is the key, the motion, the change. A static magnet sitting next to a static wire produces nothing. It is the relative motion, the cutting of magnetic field lines by a conductor, that creates the push. Let us take a moment to understand this in plain, everyday terms. A magnet produces an invisible field of force around it, a region where other magnetic materials feel a pull or a push. This field is strongest near the poles of the magnet and weaker farther away. You have seen this field made visible if you have ever done the simple experiment of sprinkling iron filings on a piece of paper placed over a magnet. The filings align themselves along the field lines, tracing out the shape of the invisible force. Now imagine taking a wire and moving it quickly through that field, cutting across those invisible lines. The electrons in the wire experience a force, a push, at right angles to both the direction of the magnetic field and the direction of motion. This push drives them along the wire, and if the wire is part of a complete circuit, a current flows. This is the basic principle that underlies every generator in every power plant, from the smallest portable unit to the largest station serving millions of homes. A generator is a machine that converts motion into electricity. It does this by spinning a magnet, or a set of magnets, inside a stationary set of wire coils, or by spinning the coils inside a stationary magnetic field. The spinning creates the relative motion. The magnetic field cuts across the wires. The electrons in the wires feel the push, and current begins to flow. The source of the spinning motion can be almost anything. In a hydroelectric dam, falling water turns a wheel called a turbine, and the turbine is connected to the shaft of the generator. The weight and pressure of the water, gravity doing its patient work, spins the magnets inside the coils, and the mechanical energy of the falling water is converted into electrical energy. In a coal, natural gas, or nuclear power plant, the process is similar, but the spinning force comes from steam. A fuel is burned, or a nuclear reaction takes place, and the heat produced boils water into high-pressure steam. That steam is directed against the blades of a turbine, spinning it at high speed, and the turbine turns the generator. In a wind turbine, the wind itself, moving across the landscape, turns the blades, and the blades turn the generator. In each case, the underlying idea is the same. Motion turns a magnet inside a coil, and the motion becomes electricity. This is a quiet, almost meditative thought. Every light that glows in your home, every device that hums softly in the dark, every screen that flickers with information or entertainment, is powered, at root, by something spinning. Somewhere, not too far away, a turbine is turning. It may be turned by steam, by water, by wind. It may be turned by the combustion of natural gas or the fission of uranium atoms. But the spinning is the common element. The spinning is what makes the electricity. The quiet, steady rotation of a magnet inside a coil of wire, a motion that has been refined and scaled up over more than a century of engineering, but that remains at its heart the same simple effect that Faraday demonstrated with his iron ring and his two coils of wire. There is another way to generate electricity, one that does not involve spinning. A solar panel, or photovoltaic cell, converts sunlight directly into electricity. It does this not by moving a wire through a magnetic field, but by using a special material, usually silicon, that absorbs the energy from photons of light and uses that energy to knock electrons loose from their atoms. These loose electrons are then collected and directed through a circuit, creating a flow of direct current. Solar panels are quiet and still. They have no moving parts. They sit in the sun and generate electricity from the steady stream of photons that falls on them. This is a different principle from electromagnetic induction, and it is increasingly important as the world seeks cleaner sources of energy. But for the vast majority of the electricity that powers the modern world, the spinning generator is still the workhorse. The turbine, the magnet, the coil, the quiet conversion of motion into push. The scale of this process is worth pausing on for a moment, because it is easy to take for granted. The generator at a large power plant is a massive machine, weighing many tons, spinning at a precise speed, often 3,000 or 3,600 revolutions per minute, depending on the frequency of the grid. The magnets inside it are not the small, simple magnets you might have on your refrigerator. They are electromagnets, coils of wire that become magnetic when a current flows through them. These electromagnets are arranged on a rotor, the spinning part of the generator, and they produce a very strong magnetic field. Surrounding the rotor is the stator, the stationary part, which contains the coils of wire in which the electricity is induced. The clearance between the rotor and the stator is tiny, often just a few millimeters, and the whole assembly is cooled by air or hydrogen or water to keep it from overheating. It is a triumph of precision engineering, a quiet giant spinning steadily through the day and night, converting the energy of steam or falling water into the electrical push that flows out through transformers and transmission lines and eventually into the walls of your home. But the principle, the core idea, remains the same as Faraday's simple experiment. Move a wire near a magnet. Move a magnet near a wire. Create a changing magnetic field. Induce a voltage. Push the electrons. The scale is different, the materials are different, the efficiency is vastly greater, but the physics is identical. This is one of the quiet beauties of settled science. The principles do not change. They are the same in a child's science fair project as they are in a gigawatt power station. The universe does not make exceptions for scale. There is also a kind of gentle reciprocity at work here, a symmetry that Faraday himself recognized. If moving a wire near a magnet creates electricity, then sending electricity through a wire near a magnet should create motion, and indeed it does. That is how an electric motor works. A motor is essentially a generator run in reverse. You put electricity in, and you get spinning motion out. The same principles apply, the same relationship between magnetism and current, the same quiet, elegant physics. Every electric motor, from the tiny one that vibrates your phone to the large ones that drive industrial machinery and electric trains, works on this same reciprocal principle. Faraday's discovery was a two-way door, motion into electricity, electricity into motion. The same door, swinging both ways. As you lie here in the dark, you might think about the spinning that is happening somewhere to make these words reach you. Perhaps it is a wind turbine turning slowly on a distant ridge, its blades catching the same night breeze that rustles the leaves outside your window. Perhaps it is a steam turbine spinning in a plant near a river, its steam coming from natural gas burned in a carefully controlled chamber, or from the steady, quiet heat of a nuclear core. Perhaps it is a hydroelectric turbine, deep in a dam, turned by the weight of water that fell as rain on a mountain months ago and has been making its slow way downstream ever since. The source does not matter, in a sense. The spinning is the thing. The spinning is what makes the push. And the push, traveling through transformers and transmission lines and the wires in your walls, arrives here, now, in the soft glow of a screen or the warm hum of a speaker, carrying the energy of that distant motion into the quiet of your room. Let that image settle. The spinning magnet, the coils of wire, the gentle, steady conversion of motion into electricity. It has been happening for more than a century, in one form or another. It happens through the night, while the world sleeps and the demand for power drops to its lowest ebb. The turbines keep turning, the generators keep humming. The electrons keep swaying back and forth in their patient oscillation, carrying the push from the spinning machines to the quiet outlets in your walls. And somewhere, in a control room, an engineer watches the dials and makes sure that the supply matches the demand, that the frequency stays steady at 50 or 60 cycles per second, that the whole vast, interconnected system remains in balance. It is a quiet, ongoing miracle of coordination, built on a principle that a self-taught blacksmith's son discovered with 2 coils of wire and an iron ring on a quiet day in London nearly 200 years ago. And the principle has not changed, and it will not change. It is settled, solid, reliable, a fixed point in the shifting landscape of technology. And as you drift closer to sleep, That reliability is a soft and welcome companion, a quiet hum in the dark, a gentle reminder that some things in the universe are constant and can be counted on, now and always. The quiet hum continues, steady and reliable. But the electricity that reaches your home does not come directly from the spinning generator. It has a long journey to make, a trip that can span hundreds of miles, crossing fields and forests, rivers and mountains, highways and small towns, before it finally arrives at the outlet in your wall. This journey is one of the great quiet achievements of modern engineering, and it is built on a simple, practical problem. Electricity loses energy as it travels through wires. The longer the journey, the more energy is lost. And so, to send electricity over long distances without losing too much of it along the way, we must be clever. We must use a trick, a quiet workaround that has been understood and refined for more than a century. Let us begin with the problem itself. We talked earlier about resistance, the gentle pushback that every material offers to the flow of current. Even the best conductors, like copper and aluminum, have some resistance. When current flows through a wire, that resistance converts some of the electrical energy into heat. The energy is not destroyed, it is just transformed into a form that is not useful for the purpose at hand, a gentle warming of the air around the wire that dissipates and cannot be recovered. The amount of energy lost as heat depends on two things. It depends on the resistance of the wire, which is determined by the material, the length, and the thickness, and it depends, crucially, on the current. The heat loss grows with the square of the current. Double the current, and the heat loss quadruples. Triple the current, and the heat loss becomes 9 times as great. This relationship means that high current is very expensive in terms of energy loss, especially over long distances. So the problem is this: a power plant generates electricity at a certain voltage. The total amount of power being sent out is the voltage multiplied by the current. To deliver a given amount of power, you can use a high voltage and a low current, or a low voltage and a high current. The product is the same, but the heat loss in the wires depends only on the current, not on the voltage. High current means high losses, low current means low losses. Therefore, the most efficient way to send electricity over a long distance is to use the highest practical voltage and the lowest practical current. This is the core insight that shapes the entire transmission grid. But there is a complication. The generators in a power plant produce electricity at a voltage that is practical for the design of the generator itself, typically somewhere in the range of a few thousand to a few tens of thousands of volts. That is a strong push, but it is not strong enough for efficient long-distance transmission. To send electricity hundreds of miles, you need voltages in the hundreds of thousands of volts. And once the electricity arrives at its destination, you need to bring the voltage back down to safe, usable levels, like the 120 or 230 volts that come out of a wall outlet. So you need a device that can change voltage, stepping it up for the journey and stepping it back down at the end. That device is called a transformer. We mentioned the transformer briefly when we talked about alternating current, because transformers only work with alternating current. That is the reason alternating current became the standard for power grids. A transformer is a simple, elegant machine with no moving parts. It consists at its heart of 2 coils of wire wrapped around a shared core of iron. One coil is connected to the source of electricity. The other coil is connected to the load, the thing that will use the electricity. When alternating current flows through the first coil, it creates a changing magnetic field in the iron core. That changing magnetic field, in turn, induces a voltage in the second coil. The magic of the transformer is that the voltage induced in the second coil depends on the ratio of the number of turns of wire in the 2 coils. If the second coil has more turns than the first, the voltage is stepped up. If the second coil has fewer turns, the voltage is stepped down. Imagine a transformer with 100 turns of wire on the first coil and 1,000 turns on the second. The ratio is 10 to 1. If you put 100 volts of alternating current into the first coil, you will get about 1000 volts out of the second coil. The voltage has been multiplied by 10. At the same time, the current has been divided by 10. The power, the product of voltage and current, remains roughly the same, minus some small losses in the transformer itself. This is the quiet, almost magical trade-off that transformers make possible. You can exchange voltage for current and current for voltage without losing much energy in the process. High voltage and low current for the long journey. Low voltage and high current for safe use in the home. The transformer is the bridge between these two worlds. Now let us trace the path that electricity takes from the generator to your home. It is a path that unfolds in stages, each one stepping the voltage down a little further, bringing the electricity closer to the safe, familiar form that you use every day. The journey begins at the power plant, where the generator produces electricity at perhaps 10,000 or 20,000 volts. Immediately, this electricity passes through a step-up transformer, which raises the voltage to a much higher level. For a long-distance transmission line, the voltage might be 230,000 volts, or 345,000 volts, or even 765,000 volts, depending on the distance and the amount of power being sent. These are the very high voltages that travel on the tall, lattice steel towers that stride across the countryside. The ones with the long insulators made of ceramic or glass, the ones that hum softly if you stand beneath them on a quiet day. The high-voltage transmission lines carry the electricity across the long middle of the journey, the open stretches between cities and towns. The wires are made of aluminum, often reinforced with a steel core for strength. Aluminum is not as good a conductor as copper, but it is much lighter, and weight matters when you are stringing a cable between towers that may be hundreds of feet apart. The voltage is very high, so the current is relatively low, and the losses from resistance are kept to an acceptable level. The towers march across the landscape, a quiet, regular rhythm of steel and wire, carrying the invisible flow of energy from the place where it is made to the places where it will be used. As the transmission lines approach a city or a populated area, they arrive at a substation. A substation is a fenced enclosure filled with transformers, circuit breakers, and other equipment, all arranged in a neat, orderly fashion. Here, the voltage is stepped down for the first time. The very high transmission voltage, perhaps 230,000 volts, is reduced to a lower subtransmission voltage, perhaps 69,000 volts or 34,500 volts. This lower voltage is still far too high for direct use, but it is more manageable for the next stage of distribution. The subtransmission lines carry the electricity closer to where people live and work. They run along shorter towers or stout wooden poles, often alongside roads or railway lines. They feed into smaller substations, perhaps one serving a single neighborhood or a large industrial facility. At these substations, the voltage is stepped down again, this time to the distribution voltage that runs through the streets and past your house. In many places, this distribution voltage is around 7,000 to 13,000 volts, though the exact number varies depending on the local standards and the age of the infrastructure. The distribution lines are the ones you see most often, the wires that run along the wooden poles in older neighborhoods or through underground cables in newer ones. These lines carry the electricity to the final stage of the journey, the small transformers that sit on poles or on concrete pads at ground level. These are the transformers that you might have seen without ever quite knowing what they were. The cylindrical metal cans, often gray or green, that hum quietly to themselves on utility poles. The boxy green cabinets that sit on small concrete slabs in the yards of suburban homes. These are the distribution transformers, and they perform the final voltage step down. They take the distribution voltage, perhaps 7,200 volts, and reduce it to the 120 or 230 volts that your home uses. From the distribution transformer, the electricity travels through the last few feet of wire, the service drop, to your electric meter, and from the meter into the main breaker panel inside your home. and from there, it fans out through the parallel circuits we talked about earlier, through the wires hidden in the walls, to the outlets and switches and light fixtures in every room. The journey is complete. The electricity that began as a gentle push of electrons in a spinning generator, perhaps hundreds of miles away, has arrived at your bedside, quiet and ready, at the right voltage and the right frequency, to power the small device that speaks these words into the dark. This whole system, from the generator to your wall outlet, is called the grid. The electrical grid is one of the largest and most complex machines ever built. It spans entire continents. It connects thousands of power plants to millions of homes and businesses. It is constantly monitored and adjusted, second by second, to keep the supply of electricity exactly matched to the demand. If the balance is not maintained, the frequency can drift, and equipment can be damaged. The grid is a living, breathing system, a vast, slow, synchronous pulse of alternating current, with every generator spinning in lockstep, every transformer humming at the same frequency, every light bulb glowing to the same quiet rhythm. The grid is also remarkably reliable, given its complexity. Most of the time, most of us never think about it at all. The lights come on when we flip the switch. The outlets deliver power when we plug something in. The grid fades into the background, a silent, invisible infrastructure that we take for granted. And that taking for granted is, in its own way, a tribute to the engineers who designed it and the workers who maintain it. They have made something enormous and intricate feel as simple and dependable as turning a tap for water. As you lie here, drifting further into the quiet of the night, you might picture the path that the electricity took to reach you. The spinning generator, turning somewhere in the dark. The step-up transformer, raising the voltage for the long haul. The tall towers striding across the open countryside, their wires catching the starlight, a quiet line of steel and aluminum crossing fields and rivers. The substations, one after another, stepping the voltage down, bringing it closer to human scale. The pole outside your window, with its own small transformer, humming its low, steady note, and finally the wires in your walls, the outlet near your bed, the small device that glows softly beside you. It is a long journey, but it happens in an instant, at nearly the speed of light. The push is always there, waiting, patient, ready. The loop is closed, the circuit is complete, and the electricity flows, quiet and steady, through the dark. The electricity flows, quiet and steady, through the dark. But there is another way that electricity comes to us, a way that does not involve spinning generators or long transmission lines or transformers on poles. It is a way that is smaller, more personal, more portable. It sits in a drawer in your kitchen or inside the remote control on your bedside table, or in the phone that is perhaps resting near you now, its screen dark, its battery quietly holding a charge. This is electricity stored in a small container, ready to be released at the moment it is needed. The container is called a battery. A battery is a familiar thing. We use batteries every day, often without thinking about them. But a battery is also a subtle and interesting thing, because it does not work the way many people imagine. A battery is not a tank full of electricity, waiting to be poured out. It is not a jug of electrons. Electricity is not a fluid that can be bottled and stored like water or gasoline. A battery is something different, and understanding what it actually is, what it actually does, can be a quiet and satisfying thought to carry with you into sleep. What a battery contains is not electricity itself, but the potential for electricity. It contains chemicals, two different materials, chosen because they want to react with each other. They have a chemical desire, a tendency to exchange electrons. One material wants to give up electrons, the other wants to accept them. If you were to mix these two materials directly together, they would react, electrons would flow, heat would be released, and the reaction would be over in a short time. But in a battery, the two materials are kept apart. They are separated by a barrier, a material that allows certain charged particles to pass through, but not others. This separation is the key to the whole device. Because the two materials are separated, the reaction cannot happen directly. The electrons cannot jump from one material to the other. They need a path, and the battery provides that path, but only on its own terms. The battery has two terminals, two metal contacts on the outside. One terminal is connected to the material that wants to give up electrons. The other terminal is connected to the material that wants to receive them. If you connect a wire, or a light bulb, or a motor, or any other device between these two terminals, you complete a circuit. You give the electrons a path, and they take it. They flow from the negative terminal, through your device, doing work along the way, and back to the positive terminal, where they are accepted by the material that wants them. The chemical reaction proceeds slowly and steadily, and the flow of electrons, the current, continues for as long as the reaction can be sustained. This is what a battery does. It uses a controlled chemical reaction to create a push, a voltage, between its two terminals. That push is steady and reliable, at least for a while. The voltage of a battery depends on the materials used in its construction. A typical alkaline battery, the kind you might put in a flashlight or a television remote, produces about 1.5 volts. A lead-acid car battery produces about 12 volts, made up of 6 individual cells of about 2 volts each, connected in series. A lithium-ion battery, the kind in your phone or laptop, produces about 3.7 volts per cell. These voltages are not accidents. They are determined by the chemistry, by the specific materials that are chosen to give up and receive electrons. As the chemical reaction proceeds, the materials inside the battery are slowly used up. The material that gives up electrons is gradually consumed. The material that receives them is gradually filled. Eventually, the reaction slows down, the push weakens, the voltage drops, and the battery is said to be dead. It has not lost its electricity because it never contained electricity in the first place. It has used up its chemical fuel. The potential for push has been exhausted. The battery must be replaced, or, if it is the rechargeable kind, it must be connected to an outside source of voltage that will push the electrons back in the opposite direction, reversing the chemical reaction and restoring the materials to their original state. A rechargeable battery is a quiet marvel of chemistry and engineering. It uses a reaction that can be run in both directions. When you charge the battery, you force electrons to flow in the direction they do not naturally want to go. You push them back onto the material that normally gives them up. You rebuild the chemical fuel. This process is not perfectly efficient. Some energy is lost as heat with each charge and discharge cycle. Over time, the materials degrade. Small internal changes accumulate. The battery can hold a little less charge with each cycle. Eventually, even a rechargeable battery wears out. But for hundreds or thousands of cycles, it can be filled and emptied, a quiet, reversible chemical rhythm inside the device in your pocket or on your nightstand. The deep chemistry of different battery types varies a great deal, and it is not necessary to go into all of it here. The chemistry of a lead-acid car battery is different from the chemistry of an alkaline household battery, which is different from the chemistry of a lithium-ion phone battery, which is different from the chemistry of a nickel-metal hydride rechargeable battery. Each type has its own voltages, its own energy densities, its own charging requirements, its own advantages and disadvantages. The details are complex, and they are the subject of entire fields of research and engineering, but the basic idea is the same across all of them. Two different materials, a desire to react, a separation that forces the reaction to happen through an outside circuit, a flow of electrons from negative to positive, a push that lasts as long as the fuel holds out. The history of the battery is a long and quiet one. The first true battery, in the sense of a device that could produce a steady, controlled current, was invented by Alessandro Volta, the same Italian scientist for whom the volt is named. In the year 1800, Volta constructed a stack of alternating discs of zinc and copper, separated by pieces of cloth soaked in salt water. This voltaic pile, as it came to be called, produced a steady voltage and a small but continuous current. It was the first time in human history that such a thing had been achieved. Before Volta, electricity was known only as a fleeting phenomenon, a spark from a rubbed piece of amber, a discharge from a Leyden jar, a brief, wild flash that could not be sustained or controlled. Volta's pile made electricity calm, steady, and portable. It opened the door to everything that followed. Some historians note that there may have been even earlier devices that functioned as batteries, though this is a matter of debate. The so-called Baghdad battery, a small clay pot containing a copper cylinder and an iron rod, found in what is now Iraq, and dating to roughly the 1st or 2nd century of the Common Era, has been proposed by some as an ancient galvanic cell. Others argue that it was likely used for something else entirely, perhaps for storing scrolls or for some form of electroplating that we do not fully understand. There is no firm consensus, and the question remains open. It is a quiet mystery, a small, unresolved corner of the long history of human interaction with electricity. The not knowing is part of the calm. We do not need to settle it here. What is settled is that Volta's invention was the beginning of the modern electrical age. For the first time, experimenters had a reliable source of steady current. They could study electricity systematically, without having to wait for a thunderstorm or a dry winter day. From Volta's pile, the science of electricity grew. Faraday's work on induction, Ohm's work on resistance, the development of motors and generators and transformers and all the rest. The entire electrified world can trace its lineage back to that stack of zinc and copper and brine-soaked cloth, sitting on a table in Italy, quietly pushing electrons through a wire, year after year. Today, batteries are everywhere. They are in our pockets and our cars and our medical devices and our satellites and our submarines. They range in size from tiny button cells that power hearing aids to enormous installations the size of warehouses that store energy from solar farms and wind turbines for use when the sun is not shining and the wind is not blowing. But the principle has not changed. A battery is still a device that stores chemical energy and converts it, slowly and steadily, into electrical push. It is a quiet reservoir of potential, waiting for the moment when the circuit is closed and the flow begins. Think for a moment about the battery in the device that is playing these words. It is probably a lithium-ion battery, a type that has become common because it can store a lot of energy in a small, light package. Inside that battery, lithium atoms are arranged in a layered material, a kind of crystalline lattice. When the battery is charged, the lithium atoms sit in one layer, holding onto their electrons. When the battery is discharged, the lithium atoms move to another layer, releasing their electrons through the outside circuit to do the work of powering the device. The lithium atoms shuttle back and forth between the layers, a quiet, atomic-scale dance that repeats with every charge and discharge cycle. It is a gentle rhythm, a soft chemical heartbeat, hidden inside the sealed metal case of the battery, invisible and silent, doing its work without fuss or fanfare. The battery does not last forever. Even if you are not using the device, even if the circuit is open and no current is flowing, the chemicals inside the battery are slowly degrading. Tiny internal reactions, unwanted side reactions, gradually eat away at the materials. The capacity fades, the voltage sags. Eventually, the battery can no longer hold enough charge to be useful. This is the nature of chemical storage. It is temporary, it is finite. But while it lasts, it is a quiet, dependable companion, a small container of push that you can carry with you, that you can hold in your hand, that you can rely on to bring light and sound and connection into the dark hours of the night. As you lie here, letting these words drift over you, you might think about the small battery that may be resting near you now. It is a product of centuries of quiet scientific work, of careful experimentation and patient engineering. It is a direct descendant of Volta's pile, of Faraday's coils, of the long, steady accumulation of knowledge about how materials behave and how electrons move. It is a small thing, easily overlooked, but it is also a quiet triumph, a portable piece of the electrified world, sitting silently in the dark, waiting for the moment when you will press a button and close the circuit and let the push flow once more. And that thought, too, can settle softly into the quiet of the room, a gentle reminder that even the smallest things contain within them the echoes of a long and patient history, a history of curiosity and understanding, of questions asked and answered, of the slow, steady unfolding of the secrets of the natural world. The slow, steady unfolding continues, even now, even as the night draws on and the last of these words make their way toward you through the dark. And as we begin the final part of our walk, the part where the path begins to turn gently back toward silence, it is worth remembering something that has been quietly present throughout everything we have talked about. Electricity is not just something out there, in the wires and the batteries and the distant generators. It is also something in here, inside you. It is part of you. It is part of every living thing. Your own body runs on electricity. Not the same kind that comes from a wall outlet, not the 120 or 230 volts of alternating current, but a much gentler, much smaller version, a soft, internal electrical language that your cells use to communicate with one another. Your nervous system is, at its most basic level, an electrical signaling network. The signals that tell your muscles to move, the signals that carry sensation from your skin to your brain, the signals that regulate your heartbeat and your breathing, and the slow, quiet work of digestion. All of these are electrical impulses. They are tiny voltages, tiny currents, moving not through copper wires, but through the long, branching fibers of your nerve cells. The way this works is similar in principle to the batteries and circuits we have been describing, though the materials are very different. A nerve cell, or neuron, maintains a difference in electrical pressure across its outer membrane. It keeps more positive ions on the outside and more negative ions on the inside, a careful, balanced imbalance that requires energy to sustain. When the neuron receives a signal, a small region of the membrane opens tiny channels, and the ions rush across, briefly flipping the voltage difference in that spot. This flip triggers the next region of the membrane to do the same, and the next, a wave of electrical change that travels down the length of the nerve fiber. This wave is called an action potential. It is a tiny, brief pulse of electrical movement, and it is the fundamental unit of information in your nervous system. These pulses travel fast, though not as fast as the signals in a copper wire. They move at perhaps a few meters per second, or in some specialized nerves, up to about 100 meters per second. That is fast enough for a thought to become an action in a fraction of a second, fast enough for your hand to pull back from a hot surface before you are even consciously aware of the heat, fast enough for your eyelids to grow heavy and your breathing to slow as you drift toward sleep. And the quiet, rhythmic signals that travel from your brainstem to your diaphragm, telling your lungs to expand and contract, continue their work without any conscious thought at all. They have been doing so since the moment you were born. They will continue to do so through the night. Through every night, a patient, tireless electrical pulse that keeps the breath moving in and out, a soft, biological alternating current of life. The heart, too, runs on electricity. In the upper part of the heart, there is a small cluster of cells called the sinoatrial node. These cells have a special property. They can generate their own rhythm. They slowly, gradually build up an electrical charge until it reaches a threshold, and then they fire, sending a pulse of voltage across the heart muscle. This pulse causes the upper chambers to contract. The signal then travels to another node, the atrioventricular node, which delays it slightly and then sends it down into the lower chambers, causing them to contract as well. This sequence, this quiet electrical choreography, is what produces the familiar lub-dub sound of a heartbeat. It happens about once every second, 60 or 70 times a minute, more than 100,000 times a day, year after year after year. It is a circuit, a loop, a rhythmic closing and opening of an electrical path. It is the same principle as the alternating current in the walls, but softer, slower, made of ions and membranes instead of electrons and wires. These facts are not meant to be clinical or detailed. They are just gentle reminders that the boundary between the electrical world outside and the electrical world inside is not as sharp as it might seem. The same force that lights a city also flickers inside you. The same push and flow, the same movement of charge from a place of higher pressure to a place of lower pressure, the same quiet seeking of balance is happening in your nerves and your muscles and your heart, even now, even as you lie still in the dark. You are an electrical creature, you always have been. The spark that jumps from a doorknob on a dry winter day is a cousin to the spark that travels down a nerve to tell your finger to move. The battery in your phone is a cousin to the chemical gradient that powers your thoughts. It is all one thing, all one set of principles, all one quiet, patient logic that runs through the universe at every scale. Let us revisit some of the images from our walk, the images that have carried us through the night. The tiny spark, the static discharge, the sudden, brief rearrangement of charge that you have felt with your own body. The balloon clinging to the wall, held by the gentle pull between opposite charges. The lightning bolt, the same idea written large across the stormy sky. The wire, the copper pathway, full of loose electrons drifting slowly, nudging each other along. The spinning generator, the magnet turning inside the coil, converting motion into push, the quiet, steady heart of the electrical world. The tall towers striding across the countryside, their wires humming softly in the dark, carrying the high-voltage current from the power plant to the substations and the transformers, and finally, step by step, down to the quiet outlet near your bed. The battery, the small container of chemical potential, waiting patiently for the circuit to close so that its stored push can be released. And the circuit itself, the loop, the circle, the path that returns to its starting point, the shape of all electrical flow, whether in a wire or in a nerve or in the beating of a heart. All of these images, all of these stories, are really one story. They are all variations on a single, simple theme, a push and a flow, a difference in electrical pressure and a movement of charge to equalize that difference, voltage and current, push and flow. Everything we have talked about, from the atom to the lightning bolt, from the battery to the power grid, can be understood in these simple, gentle terms. There is a push, a difference, a pressure. There is a path, a conductor, a circuit. And there is a flow, a current, a movement of charge, from the place where it is crowded to the place where it is scarce. That is it. That is the whole of it. The rest is detail, is scale, is application, is the patient work of engineers and scientists over centuries, building on this simple foundation, refining and expanding and applying the same basic rules in ever more sophisticated ways. And now, as we near the end of our walk, the pace can slow even further. The words can come more softly, with longer pauses between them. The night is deep, the room is still, your breathing is slow and regular, your heart is beating its quiet electrical rhythm, and the wires in the walls are humming their gentle 60-cycle or 50-cycle note. The world is full of electricity, but it is not a frightening or mysterious thing. It is a settled thing, an understood thing, a thing that operates by rules that have been known for a long time. It is a part of nature, as much as gravity or sunlight or the falling of rain. It is a force that we have learned to harness, to guide, to store, to use, but it is also a force that was here long before us, that will be here long after, that moves through the universe in its patient, predictable way, seeking balance, doing work, lighting the dark. There is comfort in that. There is comfort in knowing that the universe operates by rules, and that those rules are knowable, and that they have been known in broad outline for generations. There is comfort in the predictability of resistance, in the steady oscillation of alternating current, in the reliable voltage of a battery, in the quiet, circling flow of electrons through a closed circuit. These are not mysteries to be feared. They are patterns to be appreciated, gentle rhythms that can lull a tired mind toward rest. The same patterns that run through the wires also run through your nerves. The same push and flow, the same seeking of balance, the same quiet, patient logic. Let your thoughts grow soft and hazy now. Let the images drift through your mind like clouds across a dark sky. The spark, the wire, the spinning generator, the tall towers crossing the open land, the small transformer on the pole outside, humming its low note, the wires in the walls, hidden and quiet, the small battery, sitting on the nightstand holding its chemical potential, the tiny electrical pulses traveling through your own nerves, slower now, more relaxed, carrying the message of rest through every part of your body. All of these things are connected. All of these things are one thing: the push, the flow, the gentle, tireless movement of charge toward balance. There is nothing more to explain tonight. There is nothing more to unfold. The walk is complete. The circle is closed. The circuit of this quiet journey has returned to its starting point, and now it can rest, and so can you. Let the last images settle. Let the words fade into silence. The night is deep, the world is quiet, and the electricity, the same electricity that lights the stars and powers the storm and beats in your heart, continues its patient work, inside you and around you, a soft and steady presence in the dark.